Секунду, начинается. Вы не против, да, если рекординг на доклад?
Сергей Степанович.
Сергей.
Если запись доклада будет вестись, вы не против?
Ага,
Нет, конечно.
Хорошо, спасибо. Давайте Коля. Ага.
Okay, so I see that Julia Knight is with us, so I will make I will make a brief introduction in English. So we have this workshop which is devoted to World Logic Day, and as you may have heard about this, that World Logic Day, the date is chosen because Alfred Tarski was born on this day in 1901, and Kurt Gödel died on this day in 1978. And logic is, so UNESCO recognized the importance of logic in the human life, and the Director General of UNESCO, Audrey Azoulay, in her speech, she says that in the 21st century, the discipline of logic is a particularly timely one, utterly vital to our societies and economies. Computer science and information and communication technology are rooted in logical and algorithmic reasoning. So, as you can see, we now can use these digital technologies because of the pandemic, and we used this chance to organize a joint online workshop organized by Sobolev Institute of Mathematics in Novosibirsk and Nazarbayev University in Nur-Sultan. So I would like to thank our speakers for agreeing to give talks about. I would like to thank all the participants for participating in this event. And maybe Manat also wants to say a couple of words.
Yes, thank you for all, and let's wish everyone happy and okay, so I think we have only 1 minute, right? Thanks again.
Okay, thank you. And our first talk today will be a talk by Sergey Goncharov, an academician of Russian Academy of Sciences and the director of Sobolev Institute of Mathematics. And his talk will be about mathematical logic and its applications. And I think the talk will be in Russian. Yes?
Yes.
Okay. So please, okay, thank
you.
Yes.
Thank you very much for the invitation of this World Logic Day. And I would like to say several words. Прежде всего я хочу сказать, что вот по решению ЮНЕСКО этот день празднуется как Logic Day, но и важность его именно в 21 веке связана с развитием информационных и коммуникационных технологий. И логика играет в развитии этих технологий довольно большую роль. Но надо заметить, что логика и в 20 веке сыграла большую роль, логика и теория вычислимости. Дело в том, что как раз создание языков программирования и возможности создания языков программирования, они как раз и восходят к работам Gödeля, Тарского и других, Клини, Чорча, Тьюринга, которые дали возможность именно создать довольно широкие возможности. Но в 20 веке в большей степени внимание было привлечено к вычислительной математике, именно к математическому моделированию различных физических процессов, связанных и с ядерной энергетикой, и с космосом, ну и с другими проблемами, рядом других проблем. Но вот в 21 веке как раз информационные и коммуникационные технологии развиваются, и мы действительно, вот то, что сказал Николай Алексеевич, имеем возможность воспользоваться ими для того, чтобы организовать такую встречу. Но я еще хочу отметить, что роль логики, как отмечено вот как раз в выступлении генерального директора ЮНЕСКО, она играет существенную роль и в развитии, и в философии, то есть понимании природы, ну и в естественных и гуманитарных науках. То есть вот эта сторона логики, что наука только тогда становится наукой, когда она использует в своих исследованиях именно логику и логические принципы, и правильно обосновывает те или иные выводы. Я как раз недавно читал книгу это Ричард Фейман. Вот, он как раз отмечает, что не всегда именно в науке используется именно такой логический анализ для того, чтобы обосновать те или иные положения и анализ тех вещей. Вот логика дает как раз тот аппарат и те, так сказать, задают требования, которые позволяют это успешно решать. Ну и вот как раз это решение ЮНЕСКО об так сказать, назначении этого дня в качестве дня. Но вот еще одна сторона важная, которая отмечена в этом документе, это о том, что необходимо исследование в области логики и преподавание логики, в обучении логики. То есть вот, важность именно логики для обучения, вот тоже это важный фактор, который играет существенную роль. И основы логики, они преподаются во многих научных направлениях, но не всегда с должным вниманием относятся к этим проблемам. Поэтому я вот хотел на эту сторону логики также обратить как основа для обучения именно научного анализа тех или иных возникающих проблем. Ну, естественно, что этот день отмечается в честь как раз двух выдающихся математиков, Курта Гёделя и Альфреда Тарского, которые как раз очень много сделали для развития математической логики и того, что это произошло. Но вот прежде всего я хочу сказать о том, что Тарский был одним из основателей теории моделей. Именно он развил теорию истинности. Что такое истина? И это был важным фактором для того, чтобы построить математические модели и анализировать эти математические модели. Но и также он начал исследования в области разрешимых и неразрешимых теорий. Вот он доказал, что теории полей вещественных, лесных чисел, они имеют разрешимую теорию. И вот как раз Юрий Чершов решил одну из проблем Тарского о теории поля периодических чисел, доказал их разрешимость. Это важный фактор, который показал роль логики именно в применении к конкретным задачам. Ну и другая теорема, которая также была доказана российским математиком Юрием Матеисеевичем, это решение 10-й проблемы Гильберта, который показал, что она неразрешима, но надо заметить, что он ее доказал над множеством, вернее, над моделью арифметики. Вот проблема 10-й проблемы Гильберта над рациональными числами, она остается открытой. Но еще важный фактор, что в теории моделей ключевую роль во многих исследованиях играет теорема Мальцева о компактности. Вот эта теорема как раз в очень многих исследованиях позволяет строить новые модели с различными свойствами и является ключевым в исследованиях в области теории моделей. Ну и теория моделей является как раз той основой, которая позволяет развивать и теорию онтологии, и современную теорию информатики и компьютер-сайенс. Теперь по Курту Гёделю. Но вот Курт Гёдель, он отталкивался от тех исследований, которые были сделаны Уайтхедом и Расселом, которые построили логические системы, которые были нужны для того, чтобы работать уже с моделями, связанными с непрерывной математикой, с моделями, которые возникли и на базе построения вот как раз бесконечных, поля вещественных чисел, поля комплексных чисел. И вот для того, чтобы правильно работать с этими, необходимо нужна была строгая логическая основа. И вот эта основа была в их фундаментальном труде, она построена. Ну, естественно, это работа Чорча, Клейни, Тюринга и Поста, которые начали развивать теорию вычислимости. И вот как раз Гёдель доказал теорему о полноте для исчисления, которая была построена, это что формула совместного тогда и только, если она реализуется, счетной модели, и теорему о неполноте, о том, что какой бы мы ни взяли рекурсивно аксиоматизируемое расширение пиановской арифметики, слабой пиановской арифметики, всегда мы найдем такую теорему, что эта формула, теорема и ее отрицание не могут быть доказаны в этой теореме. Ну и при некотором дополнительном предположении о непротиворечивости была доказана вот теорема Гёделя, ну, уже Россер ее несколько, так сказать, расширил ее применимость, и применение сделал для непротиворечивых расширений арифметики пиано, что там можно сформулировать теорему о непротиворечивости этой теории в рамках арифметики и доказать, что невозможно из этой теории не доказать ни противоречивость, ни отрицание этого утверждения из этой теории. Вот. Это важный фактор, который занимает и многих философов, но и показывает о том, насколько сложна и трудна математика, и надеяться на то, что идея Лейбница о том, что можно построить алгоритм, который заменит всех математиков и будет решать все математические проблемы, она не будет решена. Но вот при доказательстве этой теоремы очень важные два фактора. Это первое. Было доказано, что теория рекурсивных функций, она определима в арифметике. Правда, он определял теорию примитивных рекурсивных функций и доказывал, что они представлены в пиановской арифметике. Но и вторая очень важная идея о том, что можно построить гёделевскую нумерацию, то есть нумерацию, в которой можно распознавать все по построению термов и формул и использовать уже такую самоприменимость арифметики к рассуждениям о теории арифметики, это самоприменимость. Вот эти два важных фактора, они легли потом и построение как раз теории вычислимых функций и построение к линии универсальной функции, потому что это ключевые вопросы, которые здесь были. Вот. И на основе вот тех результатов, которые были построены Тарским и Гёделем, вот была развита теория машин Тьюринга или машин Поста и теория частично рекурсивных линий Чорча, которые играют существенную роль в развитии вообще IT-технологий. Ну и важная теорема здесь — это теорема об универсальной функции, СМН-теоремы и теория поста сводимости, которая позволяет классифицировать и которой посвящено довольно большое количество работ в теории вычислимости, которая играет существенную роль в построении этой теории. Другое направление, которое развивается в классической теории вычислимости, связано именно в объединении идей вычислимости и теории моделей. Вот Рабином, Фрёрихом, Шеферсоном и Мальцевым была построена теория вычислимых или конструктивных моделей, рекурсивных моделей, еще как говорят, и которая получила довольно существенное развитие после 50-х годов, когда эти исследования были начаты. Ну и другое направление, это было направление, уже связанное с построением такой эффективной версии теории моделей, основанной на теории разрешимых или строго конструктивных моделей, которые были определены Ершовым и Майклом Морли, и которые также стали важным направлением в развитии и теории моделей, и теории вычислимости. Ну и теперь несколько о проблемах. Ну вот одна из таких глубоких проблем, которая осталась до сих пор нерешенной, и которая вот как раз в последнем постановлении правительства нашей страны было принято, что одной из ключевых проблем является проблема P равно P. То есть полиномиальные вычисления и недетерминированные полиномиальные вычислимость, совпадают они или нет. Вот, ну, более понятно, эта проблема состоит в том, что если мы рассмотрим булевую функцию, то есть функции, порожденные над двухэлементным множеством из нуля и единицы, над полем из двух элементов, можно сказать, термы вот в поле над этим, вот будут ли они давать тождественную, определить по терму, является ли он тождественно равным единице или нет. Вот эта проблема, можно ли ее решить за полиномиальное время. Вот эта проблема остается открытой. Но вот очень тесно связанная с этим проблематика, связана с существованием полиномиальных представлений для различных математических моделей. Вот это направление, оно тесно связано с P равно NP, но и является таким ключевым и в развитии этой теории, и тех фрагментов математики, тех теорий, которые можно применять в этом случае. И, на мой взгляд, является в настоящее время одним из важных направлений, которые предстоит еще существенно развивать и продвигать. Другая проблема, которая очень интересная, остается открытым, но вот с 70-х годов, это проблема Майкла Морли о Эйзенхойтовой теории. Если вот есть Эйзенхойтова теория, то есть теория с конечным числом счетных моделей, и все типы в ней разрешимы, вопрос состоит, а будут, ну, раз в ней всего конечного числа моделей, все типы разрешимы, то у нее всего конечное число моделей, все в ней хорошо, вот будут ли все счетные модели разрешимы? Вот эта проблема до сих пор остается открытой, и пока не нашла своего решения. Я считаю, что эта проблема очень важна. Она важна и с теоретико-модельной точки зрения. Описать строение этих моделей и на этой основе получить решение этой проблемы. Следующая проблема тоже интересная, на мой взгляд, вот тоже уже много лет она известна. Это если у нас есть теория, разрешимая со счетным числом счетных моделей. Будет ли в этом случае простая модель этой теории, но раз у нее счетное число счетных моделей, то типа у нее счетное число, есть простая модель, то будет ли эта простая модель разрешима, но относительно сложности этой теории. Ну или если теория разрешима, то будет ли она просто разрешима. Эта проблема вот до сих пор не решена, и мне представляется, что очень интересно. Ну вот не так давно Алаевым и Селивановым было показано, что для полей алгебраических вещественных чисел и поля алгебраических чисел можно построить полиномиальные представления. И вот проблема о том, о какой же сложности полиномиальное представление можно подстроить для этих полей, вот понизить эту сложность, и представляется очень важным. Но дело в том, что если удастся ее до разумного, так сказать, уровня понизить, то можно очень хорошо применять эти представления для того, чтобы строить вычислительные алгоритмы, именно вычислительные математики. Так как сложность, когда мы строим вычислительные алгоритмы на основе рациональных чисел, то возникает проблема при решении уравнений. Возникают уже для этих уравнений как раз алгебраические числа, и нужно работать либо с их приближениями, и это чрезвычайно затрудняет получение сложностных оценок. Поэтому эта проблема, на мой взгляд, очень интересна. Ну и следующая проблема интересная – это проблема эквивалентности. Ну вот проблема эквивалентности, я потом еще о ней скажу, но вот есть проблема, эквивалентность, вернее, которую определил Успенский. Эта проблема связана с следующим. Две модели будут эквивалентны, если над ними разрешимы одни и те же устойчивые относительно автоморфизмов множества. Вот, ясно, что если модели будут эквивалентны, ну, вот в смысле Мальцева, то автоэквивалентны, то у них эти проблемы будут одной и той же сложности, и когда разрешимы, одни и те же разрешимы. А вот в этом случае какие структуры могут возникать, какие модели будут устойчивы относительно эквивалентности по Успенскому, ну и целая серия тут проблем, которые являются интересными. Здесь некоторые результаты были получены в свое время Сергеем Федоряевым, но вот эта проблематика остается открытой. Ну, теперь по конструктивным моделям. Ну, конструктивные модели, так как я надеялся, что будут студенты, поэтому приготовил определение. Но это понятно, что если модель у нас это вычислимое множество, все отношения вычислимы, то модель будет конструктивной. Ну и, соответственно, в этом случае мы можем определить понятие автоэквивалентности. Если у нас есть рекурсивный изоморфизм между двумя разными представлениями. Ну и модель автоустойчива, если любые два представления будут эквивалентны. Ну и можно определить эту автоустойчивость относительно различных классов. Это можно, когда мы рассматриваем автоустойчивость относительно класса рекурсивных функций, можно относительно полиномиальных функций рассматривать, можно относительно разных классов арифметической, гиперарифметической эквивалентности и так далее. Рассматривать эти эквивалентности и исследовать эти эквивалентности. Ну и вот я хотел бы остановиться на проблеме, связанной со степенями автоустойчивости. Ну, степень автоустойчивости как раз называется наименьшая степень, относительно которой любые два вычислимых представления будут иметь рекурсивный автоморфизм. Ну, эти проблемы, нужно заметить, что если у нас модель имеет конечное число представлений и модели жесткие, то тогда есть степень автоустойчивости. Шор с коллегами они доказали, что в этом случае степень всегда гиперарифметическая. Ну и различные примеры были построены разными авторами. Но, тем не менее, вот эта проблематика, она очень интересна, какие же степени могут быть для конкретных структур, конкретных классов, вот этих степеней. Вот, я в свое время начал исследовать степень автоустойчивости для сильных конструктивизаций, относительно сильных конструктивизаций. Но вопрос был, так как в свое время Дуртайзен доказал, что если модель имеет вычислимое семейство полных формул, простая модель, то она будет автоустойчива относительно сильных конструктивизаций. Вот вопрос, а если она не является, это семейство полных типов невычислимо. Что будет в этом случае? Ну вот было показано, что есть примеры, когда как раз степень автоустойчивости будет как раз равна этой степени сложности полных формул. Николай Баженов показал, что существует модель такая, что у нее вообще нет степени автоустойчивости относительно сильных конструктивизаций, модель простая. Вот. Так. Да. Ну и эти проблемы связаны с различными другими классами. Ну вот, не так давно мы вместе с Валентиной Харизадовым и Расулом Мировым показали, что если мы рассматриваем разные почти простые модели, то их степени автоустойчивости, они не коррелируют с другим, они абсолютно независимы. Вот, и проблема степеней, если, вот вопрос такой, если у нас у простой модели, ну или почти простой модели, есть степень категоричности, верно ли, что она всегда совпадает в этом случае со степенью как раз полных формул? Или есть пример, когда она строго меньше степени полных формул? Эта проблема открытая, вот она представляет интерес. Ну, кстати, по степеням очень много других вопросов. Это связано, совпадает ли класс степеней автоустойчивости для всех вычислимых моделей и для разрешимых моделей. Или эти степени все-таки различаются. Ну и вообще, какой класс степеней вот, может быть степенью разрешимой модели, автоустойчивости разрешимой модели и степенью автоустойчивости произвольных моделей, ну, и для различных классов этих моделей это проблема. Следующая проблема, вот, которая интересна как раз с изучением нумерации. Вот Гёдель определил как раз вычислимую нумерацию, гёделевскую нумерацию для формулы термов, но вот мы можем для моделей рассматривать нумерацию, можем для разных классов рассматривать нумерации и на этих нумерациях определить понятие сводимости. Ну и тогда мы получаем такую полурешетку степеней для таких нумераций. Вот если мы рассматриваем конечное множество и рассматриваем их решетки, полурешетки вычислимых нумераций, то вот Юрий Чершов доказал, что эти полурешетки будут вычислимы. Вот вопрос, однако, остается здесь такой. Если мы рассматриваем вычислимые только нумерации, вычислимо-перечислимых множеств, если мы возьмем вот эту полурешетку вычислимых нумераций, это будет верхняя полурешетка, вот в этой полурешетке может ли быть только точно два минимальных элемента? Ну и вообще вопрос для любого, может ли быть конечное число минимальных элементов в полурешетке для семейства рекурсивно-перечислимых множеств. Ну, понятно, что если конечное число вычислимо-перечислимых множеств, то есть наименьшая нумерация, то есть один элемент. Значит, если код Фейвер есть, то это бесконечное семейство. Вот с вычислимыми нумерациями для конечных семейств Денисов в свое время доказал, что если мы рассматриваем семейство, в котором есть наименьший элемент и конечное число элементов несравнимых над этим наименьшим элементом, и рассматриваем нумерацию вот этих, вычислимую нумерацию этих множеств, то эти полурешетки будут изоморфны. Юрьевич нашел довольно сильные условия, когда эти полурешетки будут не изоморфные, но и вот, открытая проблема, это проблема Юрьевича Ершова. Вот если мы берем вот эту полурешетку, вернее, берем множество конечных рекурсивно перечисляемых множеств и выбрасываем из них максимальные элементы, и вот если без этих максимальных элементов эти частично упорядоченные множества будут изоморфны, то будут ли соответствующие полурешетки изоморфны? Это открытая проблема вот, в этом направлении. Ну, полурешетки можно определять и для различных классов, но вот можно определить для классов рекурсивно перечисляемых множеств. Вот в свое время мы с Андреем Сорби начали исследовать эти вычислимые нумерации, показали, что для разных уровней, если мы рассматриваем эти вычислимые нумерации, то если разница между n и m больше, чем единица, то это, вернее, больше двух мы показали вначале из Бадаева, а Подзоров потом снизил до, что если больше единицы разница, то соответствующие классы полурешеток, они будут не изоморфны. Вот. Но вопрос об элементарных теориях этих классов, он остается пока открытым. Ну и для других полурешеток, для других иерархий соответствующие проблемы также являются интересными. Вот довольно интенсивно в последние годы исследуется класс иерархии Ершова. Вот здесь получен ряд интересных проблем, но вот хотел бы отметить такой результат Бадаева-Лемпа, что есть полурешетка, в которой точно две фридберговских нумерации у семейства сигма 0,2 множеств, сигма минус 1,2 множеств вот, в иерархии Ершова. Ну и ряд других результатов по связи вот, интересно получен. Но вот вопрос о том, можно ли для какого-то семейства построить в иерархии Ершова, ну, не единичное, а вот на следующих уровнях, с конечным числом фридберговских, с конечным числом вычислимых нумераций семейства, бесконечное семейство, ну или конечное семейство, вот, не единичное. Эта проблема остается открытой. Вот мы много лет занимались, но так решение получить не удалось. Другой интересный класс вычислимых объектов – это вычислимые функционалы конечных типов. Юрием Ершовым вот это была построена как раз, была известна только вычислимые нумерации, вернее, вычислимые функции и вычислимые операции над вычислимыми функциями. И вот вопрос о том, как построить более высокие функционалы вычислимые, это была проблема. Вот Юрию Ершову удалось решить эту проблему, но это комбинация методов и из топологии, и из анализа, и из теории вычислимости, и из теории вычислимых нумераций были построены вот классы вычислимых функционалов. И доказывалось, что в каждом из этих классов есть вычислимая нумерация. Вот Сергей Оскачев показал, что в этих классах есть еще и фридберговские нумерации. Но вот общая теория вычислимых функционалов, языки для работы с этими вычислимыми функционалами, для построения функционалов, описания их свойств, вот эта проблематика пока недостаточно развита и, на мой взгляд, очень важна, потому что вот когда мы хотим применять вот в современный компьютер-сайенс различные онтологии и строить более высокие, так сказать, над ними конструкции, то там как раз возникает необходимость работать с вычислимыми функционалами. И вот правильно работать с этими функционалами, правильно анализировать их свойства, верифицировать эти свойства, построить логику для верификации этих свойств. Это представляется, на мой взгляд, очень важным направлением. И вот я считаю, что это направление необходимо всячески поддерживать и развивать. Следующее направление, о котором я хотел бы остановиться, это проблематика, вот, связанная с таким обобщенным понятием вычислимости. Юрием Ершовым была построена теория вычислимости над абстрактными структурами. Для построения этой теории он использовал как раз такое наименьшее допустимое множество, состоящее из наследственно конечных множеств. То есть мы берем модель, надстраиваем над ней наследственно конечное множество, берем отношения множественные на них и определяем класс дельта-0 функции с ограниченными кванторами и сигма-функции соответствующие. И вот в рамках этой теории можно построить хороший аналог теории вычислимости, с помощью которых можно исследовать эти классы. И если в основе модели мы берем конструктивную модель, то та вычислимость, которая строится, она дает в точности как раз вычислимые функции, вычислимые функционалы. Вот. И Юрий построена над такими моделями не только теория вычислимости, но и теория функционалов. И, вернее, даже не функционалов, а там необходимо строить теорию вычислимых отношений конечных типов для того, чтобы построить, потому что там не всегда есть универсальная функция, но всегда есть универсальные отношения. Вот это эти исследования очень интересные, ну, есть ряд интересных проблем. Но вот одна из проблем связана с проблемой построения. Вот если мы берем поле комплексных чисел и берем над ними соответствующую надстройку наследственно конечных множеств и определяем в этой надстройке сигма-определимую модель, которая будет изоморфна в нашей модели, нашему базовому полю комплексных чисел. Вот существует ли вычислимый сигма-определимый, соответственно, изоморфизм, который будет определять между ними изоморфизм. Ну и проблема вот построения таких моделей над этим полем новых моделей. Это интересное направление, но над вещественными числами, вот этими моделями исследованиями занимается ряд наших математиков. Вот Андрей Сергеевич Морозов работает в этом направлении очень активно. Но я думаю, что все об этих результатах знают. Но вот я хочу остановиться на другой стороне. Вот для применения в области компьютер-сайенс мы в свое время с Юрием Ершовым и с Дмитрием Ивановичем Свириденко предложили рассматривать уже не наследственно конечное множество, а рассматривать над ними наследственно конечные списки. Ну и, соответственно, списки над моделью, конечные списки, списки над конечными списками элементов модели и так далее. И в этом случае можно также определить структуру, и над этой структурой взять лисповские операции и в этой модели определить соответствующие аналоги дельта-0 определимости, дельта-0 формулы, сигма-формулы и определить теорию вычислимости. Но вот эти модели друг друге, как было показано в дальнейшем, определимы, и с точки зрения вот общей вычислимости они в каком-то смысле близки, но если мы рассматриваем естественно конечные списки, более того, если наша модель определена на некоторой модели конечной сигнатуре, то можно определить уже HF-модель как в нашем обогащении нашего языка некоторыми конечным числом символов и определить вот эти списки, наследственно конечные списки над этой моделью и определить здесь не только вычислимость, но и аналог полиномиальной вычислимости. Вот. И исследовать полиномиальную вычислимость и сложностные такие вопросы над этими моделями. И применять вот эти уже конструкции для того, чтобы строить программистские системы, вот о которых я скажу позже. Ну вот, здесь можно показать, было показано, что эти надстройки, они являются конструктивными моделями, и то, что определимо, оно определяет конструктивные модели. Вот. А вот дельта-0 формулы, они обладают тем замечательным свойством, что если наша модель полиномиальна, то для любой дельта-0 формулы ее проверка истинности на элементах соответствующей настройки, она будет полиномиальной. Ну, зависит от квантовой приставки из ограниченных квантов. Это сложность. Вот. Ну и вот в рамках этой теории мы можем строить уже различные антологии, объединять эти антологии вместе, потому что мы можем рассматривать многоосновную модель, где есть разные фрагменты тех или иных теорий, рассматривать взаимоотношения между этими моделями, и в рамках этих моделей строить системы для управления сложными объектами. Ну и вот я хотел бы отметить очень важные результаты, которые, я уже говорил про Лаева Селиванова, о том, что для поля вещественных чисел можно построить полиномиальные представления, и так что проблема разрешимости этих полиномиальных, нахождения полиномиальных решений для этих начальных будет полиномиальным. И очень важное применение, которое нашли эта теория вычислимых алгебраических чисел Селиванов, Виктор Львович и Селиванова Светлана Викторовна, для решения проблемы Годунова, что если, правда, это в органичном классе уравнений Каши, тем не менее мы можем в этом случае по точности, которая нам требуется от решений, задать точность, какой точности должны быть начальные данные. Ну, естественно, когда мы решаем проблему управления движущимся объектом, то для него нам нужно с определенной точностью. Если автомобиль движется, то он должен вписаться в тот или иной поворот, а если он выскочит, то он улетит в пропасть. Поэтому вот такого типа задачи, они очень важны именно в теории управления. И поэтому ту точность задания для решения тех или иных задач, она очень важна. Ну и теперь вот подходы. Так, что-то у меня перескочило. Да. Да. Ну, проблемы, которые мы можем решать. Вот, на базе как раз теории сигма-формулы и дельта-0 мы можем задавать спецификацию той задачи, которую нам нужно решить. И используя различные методы логические, как из теории вычислимости, так и из логических вычислений, мы можем находить решения. Вот очень интересно в этом отношении, в свое время это была построена теория Колмогорова о том, что семантика для интуиционистской логики, конструктивная семантика для интуиционистской логики. А вот Кайзель показал, что в случае, если есть доказательства в интуиционистской логике существования какого-то элемента, то мы можем построить термин в этой логике, которая реализует данное решение. То есть, и вот эти методы были применены, например, Туringу для некоторых решения некоторых задач, вот, раз связанных с теорией управления. И вот это один из способов. Другой способ вот был предложен как раз Витяем Евгением Евгеньевичем, который предложил рассматривать теорию квазимногообразия, можно сказать, но не просто квазимногообразие, а квазимногообразие с некоторой вероятностью. И построить для этих вероятностей исчисления, вот с помощью этого исчисления мы можем строить и находить решение с заданной точностью. Причем эта теория получается непротиворечивой. Ну и вот в последние годы очень такое большое внимание уделяется построению систем искусственного интеллекта. Ну, а система искусственного интеллекта — это, естественно, задачи, связанные с построением теории управления. Ну и слишком много надежд на то, что можно решать эти все проблемы. Ну вот здесь приводится как раз то, сколько мозг потребляет энергии, сколько современный суперкомпьютер требует энергии для того, чтобы решать некоторые задачи. Ну и вот поэтому для развития вот систем искусственного интеллекта, с нашей точки зрения, очень важна такая школа по искусственному интеллекту, которая бы объединяла исследования как в области философии, построение тех онтологий, для которых философских онтологий, тех основ, тех или иных теорий, для которых мы хотим решать те или иные задачи, правильно формулировать те задачи, которые, вот, кстати, очень важно для построения правильной постановки задач. Вот является задачный подход, который был развит Ершовым и Самохваловым, метод задач. И затем уже на основе этих философских таких онтологий построение математических моделей для этих моделей, используя еще и соответствующие наши знания об анализе тех данных, которые мы получаем, построение технологических платформ на основе различных систем, которые могут быть применяться, ну и применение вот в самых разных областях соответствующих исчислений. Ну, время у меня уже заканчивается. Я хотел бы остановиться на 4 системах, которые разрабатываются. Но вот, это система, которая разрабатывается Thailand Company, это Гумировым Виталием, это компания, которая работает в Новосибирске. Она разработала некоторую систему разработки вот таких систем управления на основе как раз комбинации методов семантического программирования, на основе обобщенной вычислимости и методов вот, исследования логических систем, вот, витяевского подхода. Система Discovery была предложена как раз Витяевым, и построена соответствующая программная система, которая применяется, и этот индуктивный вывод, и prediction, применяется для решения различных финансовых проблем и задач из гипотетики. В Иркутске профессором Манцевадой с его учениками в его центре разрабатывается B-системы, тоже основа некоторая, которая также базируется вот на дельта-0 определимости, и строится система для решения различных задач финансовых управлений, системы управления различными процессами. Вот. И система, это система, которая была разработана профессором Загоруйко в его отделе, к сожалению, недавно он ушел, и теперь продолжается профессором Беликовым. Это система Pattern Recognition, Classification, кластеризации, которая применяется для анализа данных. Эти системы как раз разрабатываются совместно с сотрудниками Института математики. Ну, вот эта система, которая была разработана Витяевым для анализа генетической информации, ну, и экспертная система, но и вот она же применяется, основанная на Expert Discovery System, применяется и для финансового анализа. Есть книга, которая есть. Вот другая система — это вот последняя разработка, которая для фирмы Slata на основе B-системы вот, предлагается система, которая используется для анализа данных и принятия решений, для управления вот большой системой, ну, компанией Slata, которая работает в Иркутском регионе. Ну и ряд других приложений. И вот эта система, которая была разработана как раз в компании Eyeline Company, и некоторые применения. Но вот я хотел бы про эту систему чуть больше сказать. Вот если нам нужно определить некоторую, так сказать, стратегию построения решения для движения нашего там автомобиля, найти путь, если мы будем описывать каждое его движение по этому пути, это будет довольно длительный процесс и очень сложный процесс. Если же мы опишем правила, как должен он в сложных ситуациях этот автомобиль двигаться и какие принимать решения, то тогда мы можем выбрать путь наиболее оптимальный, зная там, трафик, зная длину тех или иных путей и те или иные возможности, то есть в зависимости от тех приоритетов, которые нам заданы нашей спецификацией, выбрать этот путь и двигаться по этому пути, ну, применяя вот эти правила. Ну и вот эта система, она была на основе Eyeline Company, была применена для различных сервисов, для МТС. Она же применялась для компании Beeline. Вот. Эта система нашла свое применение для систем вот, различных правил организации трафика. Это для филиппинской соответствующей телекоммуникационной компании. Так. Ну и в Нигерии также применяется эта система, но уже решение других задач, где очень много различных мобильных компаний, и взаимодействие между этими компаниями вот на основе этой системы было реализовано, и эти методы применяются. То есть вот те логические методы, которые разрабатываются, они уже находят интересное приложение, но для того, чтобы их сделать более широко понятыми, необходимо еще активное, так сказать, продвижение вот этих логических методов в информатике среди студентов, которые занимаются информатикой и построением и решением соответствующих проблем в искусственном интеллекте и построению систем управления и решению различных других проблем. Так, ну, теперь вот это те эффекты, которые были достигнуты. Да, вот я хотел бы на одну сторону обратить внимание, что если мы строим эту систему на основе как раз экспертной системы, логической системы, которую задают эксперты, которые устанавливают правила, как должна работать система в тех или иных ситуациях, то тогда, не обращаясь к программистам, а работая только с экспертами, которые задают эти правила, автоматически это новые правила, новые изменения, они включаются. А так как система требует постоянных вот таких локальных изменений, и если делать эти изменения на базе программной системы, это вызывает колоссальные затраты, потому что нужно перестраивать всю систему программы. Использование такой логической системы и построение логической основы для этой системы, она позволяет уменьшить. Ну, во-вторых, эта стоимость построения таких систем, она значительно более надежна и значительно, получается, более верифицируема с точки зрения применения. Ну, а поле применения для таких методов, оно довольно вот огромно. Вот, здесь как раз предложены те области, где такие задачи требуют решения. Это система управления сложными объектами, и система телекоммуникаций, security. Но естественно, что вот эти методы, они должны комбинировать разные методы, которые развиваются в логике. Это и одна из проблем – это развитие систем, которые бы комбинировали логические и вероятностные методы. Потому что очень много данных, когда у нас не заданы точные данные, но у нас заданы некоторые системы, которые задают вероятностные данные. И в этом случае вот построение соответствующей learning системы и построение соответствующих верификационных систем, оно представляется очень актуальным и очень важным в современной вот этапе развития математической логики. Спасибо за внимание. Я закончил.
Спасибо. Давайте поблагодарим докладчика. Возможно, вопросы? Some questions?
То есть главная идея – это то, что логика не только важна для развития математики, для развития науки, но и в чистых приложениях, вот в современных приложениях как раз в связи с телекоммуникациями, в связи с проблемами работы с естественными языками и с верификацией тех или иных решений, она чрезвычайно важна. Вот сейчас довольно популярны методы machine learning, но вот проблема, которая возникает, это проблема в обосновании того, насколько можно доверять этим методам, насколько они надежны, насколько эти решения действительно можно применять. Но вот если мы применяем эти методы, ну, надо сказать, что еще одна сторона очень интересная, это связанные с правом проблемы, которые также должны базироваться на логике, но вот это тоже в последнее время довольно много обсуждается. А кто же будет отвечать за те принятые решения, в результате которых что-то пойдет не так? Ну, вот, например, в медицине. В медицине, если врач принимает неправильное решение, понятно, кто же будет отвечать в медицине, если мы пользуемся. Вот пока в медицине именно как предсказание или построение тех или иных предположений, тех или иных гипотез, которые могут быть, и уже врач на основе тех или иных предположений и анализа того, на основе чего эти решения приняты, принимает окончательное решение. Но вот обоснованность и верификация тех или иных принимаемых решений в этом случае чрезвычайно важна. Но это тоже проблема логики.
Спасибо. Вопросы, возможно, комментарии. Maybe some questions or comments. You can just unmute your mic and ask some question or make some comment. Okay, so let's thank our speaker again. And yes, we have 4 minutes to our next talk.
3 minutes.
3 minutes, yeah.
Okay.
Hi, Russell.
Nikolai, Manat, good morning.
Hi. Hi.
Good
Good
evening,
morning.
I suppose.
Good
Yes.
morning.
So, shall we check if this works? I can try sharing my slides.
Yes.
Yes.
So, now I want.
Yes, this works nice. Yeah.
Okay, great. And Nikolai, I'm in full screen here, so I won't be watching the chat, but if you see questions or anything that people want to ask just to clear up, feel free to stop me and say so. Nikolai, Manat, either of you.
Okay.
Okay, thank you.
Okay. Thank you.
Much appreciated, because I don't want to be concentrating on the chat all the time.
Sure.
Manat, could you enable chat?
Really?
Actually.
Yes, that would help.
Wait. Can you check now? Is it available?
Yeah,
Yes,
works nicely.
yes, it works.
Okay. Okay. I was thinking it's too quiet. Good morning, Stefan.
Good evening.
Okay, so I think we could start. And so our next speaker today is Professor Russell Miller from Queens College and City University of New York Graduate Center. Okay, you're welcome.
Thank you very much, Nikolai and Manat. And thank you everybody for getting up or staying up late or whatever it took to watch this. It's of course sad that we cannot all be in one place, but in the middle of January, well, there are seldom full meetings anyway. So we will do this. We will celebrate World Logic Day. And I appreciate the invitation to tell you something about logic here. What I'm going to talk about is an application of computability theory. So I will use it in mostly a non-technical way to give some insight into why Lucin's theorem is true. Now, so Lucin's theorem, let me start by reminding you about that. Nikolai Nikolaevich Lusin, I just need to get that to work there, yes, proved two theorems that bear his name. One of them is more or less viewed as a theorem in logic, descriptive set theory, essentially. And the other usually comes up early in a real analysis course. The surprising thing is that this is the theorem in analysis that we are going to look at today. So just to remind you what it says, and then we will get into the computability side. It says that for every measurable function on the real numbers and every epsilon, there is a continuous function which is equal to the original f everywhere except on a set of measure epsilon. Okay, and this is better than you might have expected. Yes, f being measurable, it would have been natural to say maybe there's a continuous function that is within epsilon of f or something like this, but this is better. This says nearly everywhere up to this very small set, f and g are equal. Okay, and you can do this for any epsilon. It is not true that you could do this up to a set of measure 0. One can prove that quite quickly, even just with very simple discontinuous functions, the characteristic function of an interval or something like this. But yes, this is a nice theorem proven more than a century ago, without any computability theory. Certainly, Turing machines were totally unknown at that time. But let's talk about how we could go at it from a computability point of view. Okay, so this requires talking about real numbers, and so you have to represent them in some way or other. And the first thing that most people think of in this context is decimals. Or possibly if you're in computer science, you think of representing a number in binary. But either way, this is the standard, first idea. It was an idea that occurred to Alan Turing himself in 1936, when he first defined the notion that came to be called a Turing machine. And I don't want to assume here that people know all the technical details of Turing machines, so I will simply say, when you hear the term, you can simply think of a computer, honestly. A computer with as much memory as you want and that never crashes or anything like this, but essentially just a digital computer. So Turing defined what came to be called Turing machines. And in his initial paper, he thought that you could use them with decimals in useful ways. But within a year, he realized that was wrong, and he published an erratum. And I can summarize the erratum in 2 words here. Turing's theorem in 1937 was that decimals suck. You can't use them very well. Now, the theorem, of course, said something more specific than this, and Turing did not use these exact words, but it does imply this eventually, and we'll talk about why. Turing proved that there is no computer that, when you give it decimal representations of any 2 real numbers that you want, outputs a decimal representation of their sum. Okay? And you would sort of think that computers should be able to add real numbers. In fact, you might think they should be able to add decimals. But, well, the theorem here is that they can't. And there is a nice, fairly quick proof of this. So let's prove that computers can't add decimals. Suppose you have a computer which you think can do it. I'm going to give it, now there are many, many examples that we could choose. I just picked one more or less at random here. I'm going to give it the following addition problem that you see with 2.35555 and 1.14444. Now, first point, the sum of these is 3.5. And if the computer wants to output 3.4999 with 9s forever after that, or 3.5 with 0s forever after that, I would accept either one, right? And those are both representations of 3.5. So let's suppose that the computer gives us one or the other of those. It begins with either 3.4 or 3.5, because anything else would certainly be wrong. And the insight here is, okay, a computer running on this and giving you 3.4 or 3.5 after finitely many steps can only have looked at finitely much of its input during that time. So if you know the definitions, we're talking, of course, about the use of the computation. So we call that number U, and the number of digits that it went through in the input before it said, aha, the sum begins with 3.4 or or 5, whichever. And now, having run the computation and found that number u, I will now run the same computer on each of the following 2 problems. They look the same, you know, for the first u decimal digits, but then after that, they're different. And in particular, the first one here is different in a way that the answer has to begin with 3.4. The second one is different in a way that means the answer has to begin with 3.5. The difference comes as soon as you get past the digit number u. I do it that way just to piss off the computer. You know, if it had looked one more digit, it would have known what to do. But anyway, the computer will give the same output on both of these problems, right? The same output that it gave the first time, because as far as it can tell, as far as everything it looked at, it sees exactly the same input. It didn't go past the end of the first u digits, okay? And for one of those, it's wrong, right? I mean, the problem on the left has to have an answer beginning with 3.4. On the right, it has to begin with 3.5. And so the computer messes up on one or the other of these, clearly. Okay. So computers can't add decimals. Okay. Those 2 slides by themselves, incidentally, make a very nice undergraduate talk or high school talk. You know, people can understand that. It's a good example to know. But let's see. Okay, computers can't add decimals. That doesn't necessarily prove that decimals suck, right? Which was what I claimed and what Turing ultimately concluded. It could be that computers suck. You know, it could be that addition is somehow just beyond computers, but that is not the case. Computers can add real numbers if we represent the real numbers in a better way. Okay, so go back to the drawing board here and we say, all right, what's a better way of naming a real number? And if you are a logician, it's very natural to think of, first of all, Cauchy sequences, and second of all, Dedicant Cuts, right? The 2 basic ways of defining the real numbers from the rationals. Okay, so Cauchy sequences, first of all. A Cauchy sequence, of course, is a sequence of rational numbers that converges, so an infinite sequence, a countable sequence that converges to a particular real. You can define this without knowing the real at first, just by saying that the rationals form what we call a Cauchy sequence. And one can view that as a representation of the limit, the x here, the boldface x. Boldface is going to mean real numbers in this talk, lightface for countable objects like rationals or natural numbers. Computationally, this is totally useless. And I'll explain why. Here comes for you a Cauchy sequence. Starts with 3. Now I'm giving you rational numbers here, but you might want to think of them as decimals, and you can do so in an obvious way. 3.1, 3.14, 3.141. You have a very good idea what sequence this is by now, 3.1415. And then, wait a second, something really weird just happened. Huh? You know, and you look at this, and I understood what was going on. What's the deal here? The reason why Cauchy sequences are computationally useless is because no finite initial segment of the sequence tells you anything whatsoever about the limit, right? I mean, I told you this is going to be a Cauchy sequence. Sure, it's going to be a Cauchy sequence. I didn't promise it converged to pi or anything like that. And just because you see a few terms that look like maybe that's the answer, doesn't mean they do. So I mean, this could converge to anything, right? And every Cauchy sequence has this property that no initial segment tells you anything about what it converges to. So you can use these, you can add them extremely easily, in fact, but there's not much point. However, there is a version that is usually used in computable analysis, the fast converging Cauchy sequence. So these are Cauchy sequences that satisfy a particular extra property. First of all, they are Cauchy sequences, so you know that some limit x exists in the real numbers. And the requirement is that for every term x sub n approximates x to within 1 over 2 to the n. Okay. Now, there's nothing too special about using 1 over 2 to the n here. Any computable sequence that of rationals that descends to 0 could serve as the bounds, but 1 over 2 to the n is nice and simple. It's what we pretty much always use. And so what that's really saying then is that when you're given a Cauchy sequence, you're really being given a sequence of intervals, right? When somebody gives you a rational number x0, as I've marked here on this number line, what they're really telling you is that the limit x lies within an open interval here. It's within 1 over 2 to the 0, either way of x0. And then when they give you x1, somewhere in here, presumably, or, they're saying, okay, they're narrowing down the interval to something shorter, right? And so they're really giving you a whole sequence of intervals. The intersection of those intervals is a single point, and that point is the x, the limit. Okay, I'm not going to try to draw any more, but you get the idea. They keep giving you this convergent sequence, and it really does converge with a known rate here. So in this case, you are getting real information about the limit x out of the sequence. Okay. I'm going to mention Dedicant Cuts here too. It is quite natural to use Dedicant Cuts. Computable analysts have mostly decided to go with the Cauchy sequences. That said, though, later in this talk, we will actually need Dedicant Cuts in a certain way, and it's part of the technical details, and I've pushed it back mostly to the end, but let's talk just a little bit about that right now. One good thing about Dedicant Cuts, okay, there's one little question. You have to say if x itself is rational, should it lie in the left cut or the right cut or neither? And when I say here strict Dedicant Cuts, I'm saying the answer is neither. So so every x has a left cut and a right cut, and if x itself is rational, then it lies in neither of those two. Okay. So that's nice because it means the representation of a real number is uniquely defined, right? For fast convergent Cauchy sequences, real numbers have a great many representations. Each one has continuum many representations. So using Dedicant Cuts might have seemed more plausible. Whether it's the same or not computationally depends on how you present the Dedicant Cuts. And it turns out that if using fast convergent Cauchy sequences, which as I said is the usual method, is equivalent to using enumerations of the two Dedicant Cuts. Okay, equivalent in the sense that there are computer programs, Turing machines, that can go back and forth between them, that can take an arbitrary fast convergent Cauchy sequence and output an enumeration of each of the left and right cuts of the limit. And in the other direction, there's a computer that can take any enumeration of the left and right cuts of x and output a Cauchy sequence that converges fast to x. Now, these two machines are not actually inverses of each other. If you start with a fast convergent Cauchy sequence and run delta on it, and then run gamma on the output, you get back some fast convergent Cauchy sequence with the same limit as the previous one. But you don't necessarily get back the same fast convergent Cauchy sequence, right? So they're not strictly inverses of each other, but they respect the limits, basically. They respect the number that's being represented. And the interesting thing, which I will probably let you try for yourself, is that if you use non-strict cuts, or if you use the characteristic function of the Dedicant Cuts, this equivalence no longer holds. You can no longer go back and forth between these. And in particular, I mean, you were hoping to get unique representation of real numbers, maybe with the strict Dedicant Cuts and with their characteristic functions, but that just is not compatible with doing computable analysis, it turns out. Now, why we think that the fast convergent Cauchy sequences are the best way and that this equivalent method, therefore, is just as good? Well, So this goes back now to the middle of the 20th century. Grigorchik gave a notion, which has come to be accepted, of computability of functions on the real numbers. Okay, and his definition used fast convergent Cauchy sequences. The idea is that there should be a computer, much like the one that we were talking about earlier, that ought to be able to do addition, a computer such that if you give it any Cauchy sequence that converges fast to any real number you like, it takes that as an oracle and computes a Cauchy sequence that converges fast to f of the limit, to f of x. Okay, and that's seems like a perfectly normal definition. This is for one variable functions. It's very simple to modify it for functions from Rn to R, and in particular, you can do this and very quickly show that addition is computable in this definition, using, of course, fast convergent Cauchy sequences. And if you know that xn and yn are each within 1/2 to the n of x and y, the limits, then of course you know how far off the sum can be from x plus y. And so basically you just use xn plus 1 and yn plus 1 and add them together to get z sub n, for the Cauchy sequence for the sum. It's a little more interesting to try to do multiplication this way, but it is quite possible. I'll leave that as an exercise. For division, the one thing that you might want to worry about is that you don't want to try to divide by 0. Okay, so if you're trying to build a Turing machine, a program which will take two fast converging Cauchy sequences, x and y, say, and output their quotient, x over y, ideally, the first thing you want to check is whether y equals 0. And that's a little more interesting. I mean, it will turn out that the equality function, the characteristic function of equality, is not a computable function in this definition. It's not possible to decide whether a given input y equals 0 specifically, or whether it equals n, or whether x equals y in general, any of this. And it should be pretty obvious if you think about it. I mean, no finite amount of a Cauchy sequence converging fast to y could possibly convince you that y equals 0, right? I mean, this is what we would call a pi1 property. It you know, finitely much information just isn't enough to tell you that. What is true, though, is that if y does not equal 0, then some finite initial segment of the fast convergent Cauchy sequence will tell you that y is not 0. Sooner or later, it will have to be so close to y that given the 1/2 to the n bounds, it tells you, aha, y is not equal to 0. So division is computable in the sense that you first check whether, you first start checking whether the second entry is 0, and if it ever proves itself not to be 0, then you go ahead and do the division. And that, you have to write a program for that, but it's not too hard at that point. If the second entry is 0, then the program just runs forever, which sort of makes sense. There's no answer, so running forever and never outputting anything is not, it seems like a reasonable thing to do in some sense. It would be nice if it would tell you that the input was 0, but that's just not true. Why equality is not computable? Well, there's a much more general result here, which says that computable functions are in fact continuous on the real numbers. Okay, this was a surprise to me when I first learned it. I would have thought you could compute, you know, simple step functions, characteristic function of the unit interval, stuff like that. I mean, when you take a real analysis course, the very simple functions, like the step functions, are regarded as so basic that it's just drilled into you. These are the things you start with, and realizing that they are not computable was kind of a surprise. this theorem, once we have it, will also prove, of course, that the characteristic function of equality is not computable, because that's not a continuous function either. So why is this? Well, we go back to the epsilon delta definition of the limit, and we say, okay, suppose you have a computable function f computed by a Turing machine, phi, a computer, and suppose that f of x0, one particular real, equals y0, fine. And we want to show that for every epsilon there is a delta, there you know the definition. Okay, so I'm going to do this for epsilons of the form 1 over 2 to the n, which is clearly sufficient. Given your epsilon, there is some, so if you could compute the output up to y sub n plus 1, whatever the output is, if you can compute it up to that n plus first term, y sub n plus 1, you know that that term is within 1 over 2 to the n plus 1 of the actual answer, y sub 0, boldface, y sub 0, right, f of x0. So, okay, so you say, well, the phi computes this function, so if I give it a fast converging Cauchy sequence for x0, at some point it outputs y0 up to yn plus 1, the rationals. And by that point, it has only looked at finitely much of the input sequence. So x0 up to xk. This is the exact same argument we made back, showing that addition was impossible for decimals. Okay, so now suppose I have some other x which has a fast converging Cauchy sequence that begins with that same initial segment, x0 up to xk. Okay, so that is to say, suppose I have some other x that's reasonably close to the first one, to the real number x0 that we started with. So every x, now there are a couple of technical details here, which I'm pushing away for the moment. Let's just go with it. Every x that's sufficiently close, within 1 over 2 to the k, roughly speaking, of little x sub k, could have a Cauchy sequence that does have a fast convergent Cauchy sequence that begins with x0 up to xk. That's where I'm fudging things just a little. You actually have to make one further step in the argument there, but let's not worry about that right now. So if I try to compute f of x using the computer phi and using the fast converging Cauchy sequence for x that begins with this same initial segment, phi is going to do the same thing it did before, with the same input up to xk. It's going to give you the same output, namely y0 up to yn plus 1. Okay, and that means then that f of x, f of this new x, right, also has to be within 1 over 2 to the n plus 1 of yn plus 1. Okay. And so putting those together, you see the triangle inequality at work down at the bottom of the slide here. F of x is within 1 over 2 to the n plus 1 of yn plus 1, which is within 1 over 2 to the n plus 1 of y0. And so ultimately, f of x minus the real number y0 in absolute value is less than 1 over 2 to the n. It's less than epsilon. And it's less than that whenever x is close enough to x0 to make x minus xk less than 1 over 2 to the k. And you have to work out what the delta is for that. It's less than 1 over 2 to the k, but it does exist and it's positive. Okay, so that's a proof of continuity, right? I mean, that's how it works. Okay, corollary, as we said, equality is not computable. All right. Natural question that you ask, well, are all continuous functions computable? And right away you say, no, forget it. That's ridiculous. There are way too many continuous functions. I mean, constant functions are all continuous, and there are continuum many of them. And whereas, of course, there are only countably many finite computer programs that you could run, so there are only countably many computable functions. And therefore, even if you're just looking at constants or linear functions, such as I have here, definitely, most of those functions are not computable. In particular, I mean, for constant functions, it's basically just a question of is it possible to compute a Cauchy sequence that converges fast to the constant? And for most constants you can think of, it is, but you can't think of very many constants. I mean, most constants do not have such a sequence. I'm going to use linear functions here as an example to show how we can salvage a theorem here, and in fact, a really nice theorem in the end. So imagine trying to compute this function c times x. Now, if you don't have a fast converging Cauchy sequence for c, you're basically sunk, right? Because for instance, when x equals 1, if you just give it the Cauchy sequence 1, 1, 1, 1, 1, 1, 1, converging to 1, the output is supposed to be c. And so if this f were a computable function, then there would have to be a computable Cauchy sequence converging fast to c, which usually is not the case. However, we can say, all right, suppose that, well, we need to know that information about this coefficient c. Let's suppose we have an oracle that gives a fast converging Cauchy sequence for c. With that, you could clearly compute this function, c times x, just because multiplication is computable, right? And so the broader definition, just relativizing to Grigorchik's definition, is to say that a function is S computable if it can be computed by a Turing machine that does the same thing as before, but it also has a fixed oracle S attached to it. So it can always ask S for information, and it can also ask questions about the Cauchy sequence for the real number x. Okay. So same definition as before, just relativized to S, right? And then the theorem, and I'm not going to try to prove this here, but it's not all that hard. It's just that everybody starts out trying to prove it the wrong way. But when you think about it, you may be able to do this on your own. The theorem is that the continuous functions on the real numbers are precisely those such that there is an oracle S which would allow you to compute the function. Okay. And now I've been a little bit cavalier about my oracles. Formally, you make them subsets of the natural numbers, and okay, that works, but informally, you often think of them as Cauchy sequences themselves, fast converging to something, or possibly some other version. You can imagine that if you were trying to compute a polynomial and several coefficients needed fast converging Cauchy sequences, then the oracle would have to give all of those. Or in fact, even for a Taylor series or something like this, you might have to give countably many fast converging Cauchy sequences, but all of that can be compressed into a single subset of natural numbers just by appropriate coding. So yeah, so you get an awful lot of functions this way, continuum many, and they are precisely the continuous functions. The proof that they are continuous is exactly the same proof as on the previous slide. You just stick in that S oracle everywhere. But yeah, so this is very cool. I tend to credit this theorem to Weyrauch, but I think it goes back further than him. He used it quite effectively in the particular context of real numbers. But it was around in the Borel theory before that, in descriptive set theory and so on. So I don't know all of the history of that theorem, but really nice theorem. Let's talk, though, about discontinuous functions, because I do want to get to talking about Lusin's theorem, which starts with a discontinuous function and produces a continuous function. If you wanted to compute the characteristic function of the unit interval, which I mentioned earlier, I thought that was a particularly simple thing, but it turns out not. What would you need to do? You'd need to answer questions such as the two that I have here. Here very specifically, the first question is asking basically, is x strictly less than 0? If it is, then there will exist an n with xn less than -1/2n, and if not, then there won't exist any such n. Second question is asking essentially the same sort of thing, is x bigger than 1, strictly greater than 1. And again, this question precisely captures that. So if you could answer existential questions about the Cauchy sequence that is given to the machine, then you could compute this characteristic function, right? You just have to ask these 2 existential questions and the answers would tell you whether to output 0 or 1. All right. So many of you know, of course, long since that what we're talking about here is the set X prime, the so-called jump of X, the set of all existential statements true about X. That is still a countable set, and so it can be viewed itself as a subset of natural numbers. And so what this slide is saying is that this characteristic function could be computed by a Turing machine, but not in the way Grigorchek defined. You have to give it more information about X, right? You have to give it the jump of X rather than merely a Cauchy sequence that converges fast to X. So I said the jump of X. You have to give it the jump of a Cauchy sequence that converges fast to X rather than just the sequence itself. Okay. And yeah, so these are not beyond the pale or anything, but they're a bit harder. It can get harder than that. So imagine once again that we're talking about a particular constant C, a real number, that has no computable fast convergent Cauchy sequence. To compute the characteristic function of C, well, you want to ask whether X equals C. For that, first of all, you need some fast convergent Cauchy sequence for C. And so some oracle S that we have here can give you that. But then you have to ask 1 quantifier questions regarding S and X together, right? The one version of it is what's written here. Is it true that for every n, Cn that converges to C and Xn that converges to X are within 1/2 to the n minus 1? That's a sufficient question to, the answer is yes, if and only if X equals C. Okay. So sometimes you have to relativize, throw in an oracle S, and then take the jump of S and X together. And sometimes, I mean, the characteristic function of the rational numbers, it gets even harder than that. For characteristic function of Q, you have to ask, does there exist a rational number such that for every n, well, such that X equals that rational, basically. And so the for all n xn minus q is saying X equals Q, and then the additional existential quantifier at the front is saying, is there a Q such that X equals Q? Is there a rational number, of course, Q, such that X equals Q? And that's no longer a 1 quantifier question, right? That requires 2 jumps because it's exist Q for all n, okay? Both quantifiers are overcountable sets, so we're very much within the arithmetical hierarchy here, but you can see that there will be times when you need more jumps. And so you can define jumps of jumps of jumps. The nth jump is the iteration of the jump operation n times. And you can actually go through all the countable ordinals. And if you want to prove the theorem, that Lucin's theorem this way, you have to go through all the countable ordinals. Those who know this will object that some countable ordinals have no computable presentation. And that's true, but since we're allowing an arbitrary fixed oracle S to be part of our computation, you can always choose an S that has sufficiently much information to give you a presentation of your ordinal, right? As long as it's a countable ordinal, which is all you have to look at, some S will suffice for that. And I'm mostly not going to worry about issues with non-computable ordinals here. I just want to focus on the main stuff here. And so, okay, so for chi sub q, you needed the second jump of x double prime, or x2. More generally, sometimes you need x to the n, or even x raised to an infinite ordinal, one of these countable jumps, of x. Okay. that leads us to the Borel functions, right? The sort of the inputs to Lusin's theorem. Remember, Lusin's theorem says for every Borel function f, there is a continuous function g, such that f and g are equal up to a set of measure epsilon. Okay. Well, now I'm definitely not going to try to prove this for you, but the Borel functions also have a nice characterization in the way that we've been doing here. A function on the reals is alpha jump s computable if exactly what we said earlier happens. There's a fixed oracle s that you can join with any fast converging Cauchy sequence for any real number x, such that if you take alpha many jumps of that join, okay, using that oracle, you can compute a Cauchy sequence that converges fast to f of x. Okay, and so the theorem is that the alpha jump s computable functions, as alpha ranges over countable ordinals and s ranges over all subsets of natural numbers, those are precisely the Borel functions. Measurable functions, Borel functions, and I'm taking that to mean the same thing here. And that's what we use to try to prove Lusin's theorem this way. So here's the statement of the theorem again. I mentioned it just now. For every Borel measurable f and every epsilon, there is a continuous g that is equal to f outside of a set of measure at most epsilon, less than epsilon. And so what we know just from these results I've been mentioning is that there's some way of, well, computing f if you have a fixed oracle s and enough jumps, alpha many jumps for some countable alpha. Okay, so there is some Turing machine phi, oracle Turing machine, which I didn't write it as an oracle here because you know the notation gets kind of hairy, but this phi should accept as oracle the alphath jump of s joined with any fast converging Cauchy sequence, and from that should compute a Cauchy sequence that converges fast to f of x. Okay, that happens, right? That's given to us. F is measurable, Borel measurable, so we've got this. So let's fix this machine phi and this particular alpha and s, and let us assume, by the way, that s does have enough information that we can talk about the alpha jump easily here. Here's the basic outline of the proof. And you know, the main thing I want to get through, again, I have some technical details which we'll talk about or not, depending on the time. But step one is that the oracle that you want to feed, you want to feed the oracle s join x to the alpha. You want to feed that oracle to the Turing machine phi. You can get that oracle usually from the alphath jump of s joined with x. Now I say usually, you can compute it uniformly and correctly except on a set of measure less than epsilon from s to the alpha join x. And so the idea of the proof is to put these two processes together, right? We want to build we want this phi from step one, we want to give it s to the alpha join x and hope that it gives back s join x to the alpha. And then whatever it gives us, which we hope is s join x to the alpha, we will plug that into phi and say, okay, phi, do your thing, compute f of x. Okay. And now, if this all works out, right? So theta is the composition of those two processes. If this all works out and we actually get a function from real numbers to real numbers, then automatically it will be continuous, right? Because, I mean, that's the theorem that we said earlier. Any function with a fixed oracle that works on just plain x, the Cauchy sequence itself, will be a continuous function, right? The problem, well, two problems. First of all, there is this set of x's where the procedure psi messes up, right? I mean, now it's a pretty small set, you can argue, a set of measure less than epsilon. again, there are some technical details here. I'll try to mention those later. But so we're allowed to be wrong, G is allowed to be wrong, to be distinct from F, on a set of measure at most epsilon. So that seems okay. What we do have to worry about, though, two things. Two things. One is that for different fast converging Cauchy sequences to the same X, we need to output fast converging Cauchy sequences for the same Y, for the same, F of X or anyway for G of X. If we want G of X to be defined, then no matter what capital X you choose for your real, you should get some fast converging Cauchy sequence with the same limit. And that, if you do, then that's G of X. Okay, so that's the first problem, is just dealing with the fact that there are all these different representations of reals. And the second problem then is what happens on the set of measure less than epsilon. I mean, if psi never converged or something like that, you'd have a problem, right? I mean, you need to output a function there. It doesn't exactly matter what it is. It will automatically be continuous as long as you manage to output something, and something that doesn't depend on the choice of the fast converging Cauchy sequence, but only depends on the limit X. Okay. Now, first thing here, I'm going to get rid of S from the argument. I mean, you can relativize everything later on. It's not very hard. If you were trying to answer questions such as, is X greater than pi? Again, that's not something that a fast converging Cauchy sequence can answer. X itself cannot answer. Also, the halting problem, right? So I'm writing it as empty set prime here, cannot answer questions like that because it doesn't know X. It doesn't know the fast converging Cauchy sequence. X prime can answer, which is why if you were trying to compute the characteristic function of the interval beginning at pi, technically you need X prime to compute that. Okay, we're trying to do a good approximation, and the idea for computing, for guessing at X prime from 0 prime join X is to use 0 prime in a sort of statistical approach. Okay, so first of all, just narrow down the field. The Cauchy sequence itself will tell you some unit length interval that has X in it. Okay, and then I want to ask whether, so, the Q that I get here could be anything. Let's say it's something close to pi to make it interesting, but it could be 3, it could be 2.5, it could be 2.2, whatever. Within the interval from Q to Q plus 1, I want to use 0 prime, as I said, statistically, to ask, first of all, do there exist initial segments of fast converging Cauchy sequences within J of total measure at least 1/2, where, I'm sorry, I just want to see this whole thing. Right. Right. Do there exist initial segments like this right. Yes, with each J, with each of them indicating that the thing is greater, that the T in question, the real number, is greater than pi. Right, I was looking for the sentence in there, but that's it. Do there exist initial segments like that of total measure greater than 1/2? Now, these segments could be arbitrary length, except they have to be finite, and there could be as many of them as you want. The halting problem can answer that question. If you search for such initial segments, will you ever find them? And so 0 prime will tell you the answer, which means it's telling you whether, within this interval J, whether the set of T's greater than pi in that interval has measure greater than 1/2 or not. Okay. And then once you've done that, you can do the same sort of thing going on to 3/4 or 1/4, depending on what the answer was the first time. And you can approximate the measure of the set of T's in J, I'm sorry, that the T's in J such that T is greater than pi, you can approximate that as closely as you want, and in particular to within the epsilon that you're given. Okay. Now, if the given x, the Cauchy sequence says x is in one of those intervals, and you say, great, it's bigger than pi, we know. If not, then you conclude that the existential formula failed, knowing that you might be wrong about that, but only on a set of measure at most epsilon. Okay. And of course, if it turns out that you were wrong, the key here is that you will eventually realize that you were wrong. So if, the only reason why you say that something is in x prime, why you guess that something is in x prime, is if you see that a computation halted. So if you say it's in x prime, then it really is. If you say it's not in x prime, you might be wrong. And it might be that 10 years later, you realize, oh, blast, it really was in x prime. You saw it halt eventually, but it's too late now. You can't go back and change your answer. What you can do, though, is sort of go into damage control at that point. So at that point, you say, okay, I just want to try to output some coherent answer for this x, and make sure that I'll get the same answer if I use different Cauchy sequences convergent fast to the same real number, to the same limit as this x. Okay. And the damage control is essentially just saying, okay, I know when I have to do this. You'll see it not just for a single x, but for an entire open interval, right? Because some initial segment of x tells you, hey, this was wrong. And you say, oh, okay, so it's going to be wrong on this entire interval. In that interval, which will fit within your set of measure less than epsilon, just try to build, a straight line approximation from the left endpoint to the right endpoint. Now, again, there are a good deal of details that have to be dealt with there, and I'm not going to go through them all here. Let's see, there's just to visualize what happens for the x greater than pi situation. Your theta with 0 prime join x guesses that if it sees that x is bigger than 3.1, if epsilon is 0.01 here, it will see that an x bigger than 3.15 is actually bigger than pi. It'll see the rational 3.15 and say, okay, x eventually got bigger than that. For the x's less than 3.15, it will guess that x is less than pi. And so it starts out building, approximating the characteristic function in a way that actually doesn't look so good. But in order just not to do anything stupid, it doesn't build these bounds on the y output right away, all the way up to 3.15. It gets closer and closer over time. But eventually, it reaches the rational number 22/7 or something like this, and it realizes that for certain things less than 3.15, it was wrong. Its approximation of x prime was wrong, and it does damage control there. It just builds something linear, essentially. So what you get might not be what you were expecting. You might have expected something that would do this kind of symmetrically around pi or so. That's not what happens. And in fact, further strange perturbations may happen between pi and 22/7, because this process will continue all the way down to pi as you go on. So you're going to get a slightly strange continuous function out of this, but you get a continuous function. And for everything bigger than 3.15, it does converge to 1. And for everything less than pi, it does converge to 0. So it's correct, except on this interval of length less than epsilon. Okay, so that's what's going on. Now, interesting conclusions that you can draw from this. First is that you can pinpoint the troublemakers here. There are specific real numbers x which just aren't going to work. Now, they form a set of measures 0. But so, okay, well, so they form a set of measures 0. The troublemakers are those x's that have, technically for which every fast converging Cauchy sequence has this alpha jump here, not computable from s to the alpha join x. Okay. Now it's known that the set of all such x has measure 0. There is no single program that computes this correctly on all the other x's. A single program can only accomplish it up to a set of small measure, arbitrarily small. So that's essentially why Lucin's theorem needs the epsilon in some specific sense. It's because you can't compute this uniformly. Okay. And the one other technical detail that I do more or less have time for, and I'll mention, we talked about unique representations and said they weren't possible. For a given x, well, there are infinitely many, many Cauchy sequences that converge fast to x, and every one of them computes the Dedicant cut of x, so they all lie in a certain upper cone, but they do lie arbitrarily far up in it. And all right, if so, the problem is that within that cone, there will be certain degrees where the bad thing on the last slide happened. Okay, so it seems like for each x, there are some approximations that cause the procedure to screw up. Now, the solution to this, first of all, you want to use the strict left and right Dedicant cuts in place of the fast converging Cauchy sequences. You can't quite compute those Dedicant cuts. What you can do is enumerate them. You can go back and forth between enumerations of the two strict cuts and fast converging Cauchy sequences. Now, so this is what I was saying. So the interesting part of this, if you simply use the fast converging Cauchy sequences, some of those sequences would have trouble making Turing degrees. And enumerations in general have the same problem, because an enumeration could have an arbitrary degree above the degree of the Dedicant cut. But there is a way to turn each enumeration into sort of a near computation of the two cuts, Lx and Rx, for the real number x. If those two cuts have a trouble-making degree, then you're in the set epsilon. But that only happens for measure 0 many x. And the way you do it is by saying, well, okay, with an enumeration, I mean, if x is irrational, then with an enumeration, you can actually compute Lx and Rx. If x were rational, then the two enumerations might leave out, would leave out x itself, which is rational. But in any case, what you can do is, at a given stage, find the first rational number in a computable list, which is undetermined so far, hasn't gone into either cut, and it's in between the gap that currently exists. And you simply say, okay, three things could happen. This Qn could later on go into the left cut, it could later on go into the right cut, or the middle possibility is that x could equal Qn, and the cuts could simply be everything less than x, everything less than Qn, and everything bigger than Qn. So you say, okay, what happens with all three of these? Run the procedure on each of those for s steps. If you get the same answer in all three cases, then that's got to be the right answer, no matter which case you're in. If you don't get the same answer in all three cases, increment s and do it again. And sooner or later, you will get the right answer for all of these. Okay, so that was the main technical thing that I wanted to get in there. I'm going to skip my very last slide, which is just other stuff, and wrap this up, because I do want to end and get Steffen Lemp's talk up next. It sounds very interesting. So thanks very much. And if there are questions, I'll certainly be happy to try to answer them.
Okay, thank you. Let's thank the speaker.
Thank you again.
So some questions. If you want to ask a question, you could just unmute your mic and say something. Maybe some comments. Pavel Ginch. Yes.
What about Lebesgue measurable functions? Have we some theorems?
Okay, so honestly, I think I'm going to have to go back and shore up my analysis before I can answer and remember everything perfectly before I say anything definite here. Yeah, this is one problem with being trapped at home right now. My real analysis books are in my office and I am here. So, let's see. The interesting thing would be to try to say, you know, how many jumps are necessary here. I think to compute a given function, right? You want to know what level of the hierarchy is it at. I mean, 0 being continuous functions, of course, and then you saw the beginnings of the hierarchy after that. I feel as though anything I say is in danger of being wrong here, though. So let me not try to say anything more specific than that. I'm sorry, but I'll see what I can work out, and if I have a better answer, I will send it to you, Pavel. So.
Okay, thank you. Maybe some other questions?
Vadim?
Yes, Vadim Grigorich.
Excuse me, Russell, what can you say about presentations by continuous fracture?
This is interesting. In fact, that was going to be mentioned just briefly on my last slide. Continued fractions also don't quite work very well. So here, I have a very low-tech board here. But if you start doing a continuous fraction, a continued fraction, you know, essentially you want to say things like this. Giving this presentation essentially means saying what are the, you know, the numbers here as you go, right? And when you make that choice, when you choose, let's say, this versus this, here you are essentially saying, is this number, let's see, if it's this, it will be less than, you know, less than 2 1/3. If it's this, it's greater than 2 1/3. And 2 1/3 itself would just end right there. So I hope that's visible here.
Yes, it's visible.
Yeah.
Okay. So the first problem is for a rational number, this just ends, and you shouldn't be able to decide if a number is rational from the Cauchy sequence, right? That's bad. So you should present continued fractions saying, okay, here's the first coordinate, here's the second coordinate, and then if it's rational, when you get to that point, you should say, you should just wait forever for the next coordinate, right? It should be undecidable. But even then, you could decide, so if you get to here and then wait forever, if that's a possibility, then this happens. But still, when you make this decision, you're deciding this. And that should not be decidable, right? You know, the characteristic function of the set of x's less than or equal to 2 1/3 should be undecidable. You know, should take one jump to compute.
Well, in other words, we cannot define whether finite this sequence or not. Yes.
First of all, you can't. If you can define whether it's finite, then you're saying whether numbers are rational or not.
Yeah.
And even if you allow sort of partial functions that have an initial segment and no more, you would still be deciding one particular side. You would still be deciding whether you're in this situation or this situation, right? For a given rational here. And that should not be decidable, right? So continued fractions are like decimals in that they make you make a discrete choice. You know, I mean, this is the problem with decimals, right? The reason they don't work is because it's 0.3, 0.3, 0.3, and then it jumps to 0.4. And there's only one point where the things can both happen. Same thing with continued fractions. You know, there's only one point where you're sort of on the cusp between these. Otherwise, you're making a discrete choice. And that's just not compatible with this notion of computable analysis. Okay, so it's a very natural idea, but it doesn't quite, it would give you a somewhat different notion of computability on the reals, and one which is not so nice in terms of saying what the continuous functions are.
Thank you.
You bet.
Okay, thank you. Yes.
Thank you. Yeah, thank you. So our next speaker is Professor Steffen Lempp from University of Wisconsin. So please, Stefan.
All right.
Great. Oh,
Let
yeah.
me just set up for a second here.
Yeah. Okay.
Give me 1 second. All right. So I hope everybody can see what's going on.
Yes.
Let's see. So it should be full screen now.
Yes.
Okay, so first of all, good morning, America. Добрый вечер, Россия, Kazakhstan. It's great to be able to celebrate World Logic Day with you, and I'd like to thank Manat and Kolya for inviting me to help celebrate this day. It's interesting that Sergey, Russell, and I chose very different topics to highlight logic, and in particular computability. I chose the topic of degree structures for two reasons. First of all, it's just over 75 years now that degree structures really became a central area of computability theory. So it's a good time to sort of look back and take stock of what's been going on in this area. Also, degree structures, degree theory, as the theory of degree structures is called, is a good area for showing that there has been a huge amount of collaboration, in particular between the countries of the former Soviet Union and the US, but also many other countries, Canada, New Zealand, various Western European countries, and so on. So it's really a celebration of international collaboration in logic. The second half of the title will become more apparent later in my talk. But what I want to focus on, on something that's sort of very classical from an algebraic point of view. Namely, we need to study an algebraic structure, such as a degree structure. One way to study structures is to look at the finite substructures, and that will help understand these complicated overall structures. So let's see. Let me start by some very simple observations. I want to first set the stage and show that this is a very general concept. So I will work with subsets of the natural numbers, denoted either by n or actually in logic usually by omega. And we're going to study these subsets under the aspect of relative computational complexity. So we will think about which, given two sets A and B, how do they compare? Can one compute the other? And so the basic definition, which has many different incarnations, is the following. We have the notion of a reducibility. This is a transitive relation on the power set of omega, such that A reducible to B expresses the fact that somehow the set B can compute the set A, where this can compute is in quotes because there are different ways of thinking about what can compute means. And I'll talk about some examples on the next slide, but let me first, given this very basic definition of reducibility in the very abstract sense, make some more definitions. So we say that two sets A and B are R equivalent if A is reducible to B and also B is reducible to A. So in some sense, that means that A and B have equal computational content. And obviously, the notion of R equivalence is an equivalence relation. So therefore, we can talk about the equivalence class of a set A, and that is called its degree. So the degree of A is the set of all subsets B which are R equivalent to A. And now we can talk about, first of all, the global degree structure. So the global degree structure is just a power set of omega, quotient, take the quotient by this equivalence relation, and then look at the partial ordering induced by the reducibility. Notice that the reducibility, since it's a transitive relation, is what's sometimes called a pre-partial order. So it's actually also reflexive, obviously. So therefore, it's a pre-partial order, whereas the lesser equal on the degree structure is, of course, a true partial order because it also satisfies antisymmetry just by definition of the quotient structure. So this is the global degree structure. But then one can also look at local degree structures. So if I take a subfamily S of the powers of omega, usually a countable subfamily, but not always, then I get the local degree structure. And a local degree structure would just be take this collection S, take the quotient by this equivalence class, equivalence relation of R equivalence, and again have the same partial ordering on it. So this sort of sets the stage for a huge number of possible degree structures that one can consider, and many of them have been considered in classical computability theory, also in theoretical computer science, and in fact even in set theory. So I want to show you a large number of examples to convince you this is an interesting that reducibilities are an interesting thing to consider. So probably the first one was the notion of M reducibility. So A is M reducible to B, or many one reducible to B, if there's a computable function which such that X is in A if and only if f of X is in B. So this is about the simplest reduction that you can think of in terms of just plain computability. In fact, this was historically probably the first one, and this is also the one that comes up in applications a lot, especially in early applications. A more complicated reducibility is that defined by Turing in the late 30s. So A is Turing reducible to B if there is a Turing functional phi such that A is computable from B via phi. Now, what that means is that there's a Turing machine which in finitely many steps, given some finite computer program, basically, and with access to an oracle B, does the following. It takes an input X, it does finitely many computational steps, each of them given by the computer program. Every once in a while, it will ask a question like, is Y in B or not? And then given the answer, we'll do one thing or the other. And after finitely many steps, it will output the answer yes or no, X is in A or X is not in A. A variant on Turing reduction is enumeration reducibility. So A is enumeration reducible to B if there is a enumeration operator phi, and that means that you only enumerate numbers which are in A, but all you're given about B is positive facts about numbers which are in B. So it's different in Turing. In a Turing functional, you have positive and negative information about the oracle, and you're outputting positive and negative information about the set A. In enumeration reducibility, you only output positive when you say, yes, this number is in A, but you can also only have access to whether or not to numbers being in B. You will never know whether a number is not in B. So this is a variant. This is very useful, for example, in computable algebra, computable model theory, and so on. And it's nowadays, I think, a well-established reducibility by itself. And then there are two variants M reducibility and Turing reducibility, which are relevant to theoretical computer science. There is polynomial time many-one reducibility, where you simply restrict the reduction for the reduction f to polynomial time functions. And there is polynomial time Turing reducibility, where you restrict the Turing functional phi to be a polynomial time functional, polynomial time in the size of the input, that is. Then going the other way, go into the to weaker reductions. We have that A is arithmetical in B. If A is first order definable in the structure of the natural number with a predicate for the unit relation symbol B, or if you like it, you can also say that A is Turing reducible to the nth jump of B for some natural number n. So that is again a transitive relation, obviously. Hyperarithmetical reducibility is the same thing, but now you have definability in a larger logic. It's not a first order definition anymore with a unit predicate for B, but it's a it is in the computable L omega 1 omega logic. Or another way of saying it is that A is Turing reducible to the alpha jump of B for some computable ordinal alpha. And then finally, at the very far end of the spectrum in set theory, you have constructible reducibility. A is constructible from B if A is in the L structure defined from starting with B and then using the usual constructible universe construction of Gödel. So all these reducibilities and many more lead to global degree structures, and oftentimes they also lead to local degree structures by restricting to certain sets. For example, in the Turing degrees, you might want to restrict yourself to the to CE sets or to DCE sets or any level of the Yershov hierarchy or delta 02 sets and so on. For enumeration degrees, you typically want to restrict yourself to sigma 02 sets or other or delta 02 sets and so on. There are a number of variations on this, and we'll get to that a little later. But notice that the local degree structures are typically considered in computability theory are generally countable. So degree theory now studies these degree structures as algebraic objects. So the algebraic objects as partial orders, right? So far, all I have is the partial ordering on the degree structure. But sometimes you also want to expand the language to include other symbols, and I'll talk about in a second. Now, the study of degree structures, degree theory, typically considers sort of what's called natural degree structures in some sense. And for natural degree structures, the typical scenario that we have is the following. First of all, there's typically a least element, something that is at the bottom of the hierarchy. So it's reducible to everything else. I mean, this is a degree which consists of the sets which are reducible to all other elements. We have that local degree structures have typically a greatest element. Global ones generally don't, but that's just that's just for the ones that are normally considered. D is typically locally countable. That means that any degree has the most countable many things below it, countable many predecessors. And that's just because there are typically only countable many reductions from a particular set to any set below it. And that's how you get the locally countable property. We also have that D is often an upper semi-lattice, but not usually a lattice. So it means there's a join operation, but usually not a meet operation. And join operation is defined quite simply as saying that the degree of A joined the degree of B is just a degree of A plus B, where A plus B is just defined by coding A on the even part of the set and B on the odd part of the set. That clearly gives for all this, in particular for all the examples I gave you, that gives a upper semilattice. Also, many degree structures support some kind of a jump operation. So Russell already mentioned the Turing jump, but it can also be the arithmetical jump, the hyperarithmetic jump, and so on. And the jump operation typically has the property that it is increasing, so A is less than A jump, and also that it's order preserving, non-strict order preserving, meaning that if A is less than or equal to B, then A jump is less than or equal to B jump. So now natural degree structures tend to be quite complicated, but they follow a pattern, at least among the degree structures that I've encountered, which is usually the following. So first of all, the first order theory of the partial order D, the degree structures, is typically undecidable. In fact, it's much worse than undecidable, namely, for global degree structures, the first order theory is typically as complicated as second order arithmetic. And when I say as complicated, I mean it's in the same M degree as second order arithmetic, as a, coding sentences of the theory as numbers. And for local degree structures, as long as they're countable, it's typically as complicated as first order arithmetic. Okay, so therefore, degree structures which were thought, in the in the first 10 years of the study of degree theory as being fairly simple, actually turned out, like this. So in the 50s and 60s, people were hoping degree structures would be simple. That turned out to be false. And it got more and more complicated. And by the 1980s, people realized that actually, degree structures are typically very, very complicated partial orders. So what do you do when you have very complicated partial orders? Well, you look at fragments of the first order theory. And the fragments are typically determined by a bound on the quantifier depth of the formulas being considered. So here is what you might do. You look at the extensional theory of D, and that is almost always decidable, because in natural degree structures, all finite partial orders embed into D. So therefore, to decide whether or not some existential sentence is true about D, all you have to decide is whether or not that sentence is consistent with the theory of partial orders. And that's a decidable fact. But it gets a little better for most degree structures. It can often be shown that the Eae theory, so the theory which only mentions sentences of form for all x vector is a y vector and then something quantifier free, can also often shown to be decidable. And I'll say a lot more about that later, because I want to focus on that, since that's an active area of research at the moment. And in fact, right now I'm working on some problems in this area. So the Eae theory is typically still decidable, but sometimes not known to be decidable. On the other hand, if you look one quantifier level further, if you look at the Eae theory, then it can often be shown to be undecidable. And I'll say a little more about how this is proved later on. But you see that typically the break between decidable and undecidable happens at when you go from 2 quantifier levels to 3 quantifier levels. And I'll explain why this is in a little bit. So let's see. So let me now try to highlight some of the degree structures. By the way, if there are questions, please do interrupt. I hear noise there once in a while. I'm not sure if these are deliberate noises or whether they are just noise coming. I can't see the chat anymore because I go in full screen. So do let me know if you have questions. Okay, so here's some results about some common degree structures, and I picked 6 degree structures which I think are the most common ones. So the many 1 degrees. So for the many 1 degrees, Lachlan showed that the theory is undecidable, And in 1980, Narod and Shor showed that actually the theory is as complicated as second-order arithmetic. On the other hand, following the pattern from the previous slide, the Eae theory is decidable. This is a result of Djuptev from 1979, whereas the Eae theory is undecidable. This is a result of Nice from 96. Similar situation happens for the CE many 1 degrees. So this is now a countable degree structure. So this was shown fairly early on to be undecidable. I think it was Lachlan again, but Nice showed that the theory of the CE many 1 degrees is the same as first order arithmetic in terms of complexity. And again, the Eae theory is decidable by the same result of Djuptev, and Nice in the same paper as for the M degrees also showed that the Eae theory is undecidable for the CEM degrees. So we have again this nice pattern: 2 quantifiers decidable, 3 quantifiers no. Moving on to the Turing degrees, we have that the Turing degrees globally. First of all, they're undecidable by early work of, again, Lachlan, I believe. Simpson in 1977 showed that actually theories as complicated as second-order arithmetic. And again, we have the same pattern. We have the Eae theory is decidable. This was shown by Lerman and Shor in the late 70s. It was written up by Lerman only a little later in his book, but Shor published a paper in 78. This was independent work of the two. Whereas the Eae theory was shown to be undecidable by joint work of Lerman and Schmerl, which appeared in Lerman's book in 83. For the CE Turing degrees, we have a somewhat less satisfying situation because we have, first of all, we have undecidability. Harrington and Schellach showed that in the early 80s. Soon after, Harrington and Slayman established that actually the theory of the CE Turing degrees is as complicated as first-order arithmetic. We only know the existential theory to be decidable. This is an old result of Sachs. We don't know about the Eae theory. I'll say some more about that later. For the Eae theory, we know it's undecidable. This is a result of me, Slayman, myself from the late 90s. There are other Turing degree structures. I only have time to give you a very small list, but I mean, there's in particular delta 02 Turing degrees. There are these levels of Yeshov's hierarchy and so on that one can say a lot of interesting things about. So I'm suppressing some work, but there's lots of interesting other work on other local degree structures within the Turing degrees that are worth mentioning. I just don't have the time for them. Moving on to the next reducibility, enumeration degrees. So the enumeration degrees were shown to have theory as complicated as second-order arithmetic by Slayman and Wooden in the late 90s. In fact, they showed undecidability and as complicated as second-order arithmetic all at once. The existential theory is decidable. This kind of, in hindsight, follows already from results of Sachs from the early 1960s, but it was formally only stated by Lagemann in 1972. The Eae theory is undecidable, and this is a very recent result which has just been submitted by Slayman, Soskova, and myself in a paper that you can find in a preprint on my webpage. I'll explain these theories, but again, notice that we don't have a decision procedure for the Eae theory. So this is still an unknown problem for the global degree structure of enumeration degrees. And then there is a local degree structure of enumeration degrees. The one that's typically considered is that of sigma 02 enumeration degrees. And we have a similar situation. Since this is a global, since a local structure which is countable, it is only as complicated as first-order arithmetic. This was shown by Goncharov and Soskova in 2012. Again, the same paper of Lagemann also showed the existential theory is decidable for this degree structure. And my former student Tom Kent in his thesis showed that the Eae theory is undecidable for the sigma 2 enumeration degrees. Again, there are other local degree structures under enumeration reducibility that are worth considering. There's delta 0, 2 degrees, etc. So there are a whole bunch of others which I am suppressing. So therefore, my apologies to people who've proved related results for other degree structures. I just didn't have time, and also I just ran out of space on this slide. Okay, so let me, before I go on, let me just mention one thing. So so there are 4 things going on. The first thing is that to show that one can code a first or second order arithmetic is usually very complicated coding argument. You have to show that you can code a model of a first order arithmetic into the degree structure, such that you can quantify over first or second order quantifiers possible within the first order theory of the degree structure. And you're only allowed to use finally many parameters. And the most important thing is you have to make sure that what you're coding is a standard model of arithmetic and not some non-standard model. This is a very complicated topic, and it would be really another talk, and therefore I'm not going to touch on this very much. I already mentioned that to show that the Eae theory is decidable is usually fairly trivial, because all you have to show is that all finite partial orders can be embedded into the degrees structure. For the Eae theory and for the Eae theory, there is a little more one can say, and I want to focus on that for the rest of my talk, because this really has to do with the second half of my title, the study of finite substructures of degree structures. So let me start with the Eae theory. So the undecidability of the Eae theory is typically shown using what's called a Nice transfer lemma. But before I state it, let me just caution that this actually goes back to work by Yashov, Lavrov, Teitzlin, and Taimanov, I believe, from like around 1960, where they showed, or somewhere in this, maybe 1970, a long time ago anyway, and where they studied the finite classes of finite structures and hereditary undecidability. This was then used, but these 4 authors did not care about the quantifier count. It was Schmerl's idea, as presented in Lerman's book from 1983. Schmerl was the one who realized that one can actually get sharp bounds on the quantifier count. And then Nice in 96 wrote a paper in which he stated this formally and crystallized really the essence of Schmerl's argument. And I'm just going to state a very special case of the Nice transfer lemma, because it's a rather technical lemma. But what it says in essence the following for the applications that we need. Suppose you have a class of finite structures, so finite algebraic structures like graphs or lattices or something like that. And suppose that I can define every structure in this class script C as a structure in the degree structure D in a way so that every atomic fact and every negated atomic fact is Eae definable. So this is important that it's definable by an extensional formula in the language of the degree structure. That's the first assumption. The second assumption I need about the script C is that the common Eae theory is hereditarily undecidable. So let me first of all stress, I need the Eae theory. Notice that, of course, the theory of C is generally not a complete theory. So therefore, you can't just talk about the Eae theory and the Eae theory interchangeably. I really need the Eae theory of C. And hereditarily undecidable here means that any consistent extension of the common Eae theory of C is also undecidable. Okay, so it's not just that the common Eae theory itself is decidable, but any super theory of it which is consistent is still undecidable. If you have these 2 conditions, extensively definable in the degree structure D, and the Eae theory of C is theoretically undecidable, then the Eae theory of D is undecidable. Now, of course, for D, of course, it doesn't make a difference whether I talk about the Eae theory, the Aea theory, because obviously the theory of a structure is going to be complete, and so it's just a complement of the other. But I just like to say it this way because that's how it's normally stated. So anyway, so this is the fact that's being used to show these undecidable results for the Eae theory. So for the structures that I mentioned on the previous slide, there were three structures: the many 1 degrees, the CE many 1 degrees, and the Turing degrees, where the class C is simply the class of all finite distributive lattices, and they're coded as initial segments. So you just need a single parameter, namely the top of the ideal or the initial segment, and that initial segment then has the order type precisely whatever finite distributed lattice you want. So that is for these 3 degree structures. For the enumeration degrees, since the enumeration degrees are downward dense, therefore there cannot be finite initial segments. So we have to be a little more complicated. This is a result that I mentioned of Slayman, Soskov, and myself. What we do is we code finite distributive lattices by 2 parameters as intervals. So all we have to tell you is the bottom and the top of the interval, and then the order type of this interval will be any finite distributive lattice that you want, and that's how you get undecidability. Because again, this is this is a very simple way to code finite structures into a degree structure. It is quite a bit more complicated for the CE Turing degrees and for the sigma 0,2 enumeration degrees. So here, what you need is the class C is actually a class of all finite bipartite lattices in a length without equality. That's very important. As soon as you allow equality, you actually lose a quantifier, so you cannot get as sharp a result. So it's finite bipartite lattice in a length without equality, and the left and the right domain of the bipartite graph has to be non-empty. And it's quite a delicate coding argument how to put this in there, because the problem, of course, is that both the CE Turing degrees and the sigma 0,2 enumeration degrees are dense partial orders, so therefore you can't expect coding by initial segments or by intervals. Has to be more complicated, and that's what makes this so hard. Okay, so for the 6 degree structures, we then have that the Eae theory can be coded in this way, and therefore is undecidable. What about the Eae theory? Well, to decide the Eae theory for a degree structure amounts to giving a uniform decision procedure to the following problem. So I fix a finite partial order P, and I fix a finite number of finite partial orders Qi, which extend P. And in the question I have to answer uniformly in P and the Qi is, does every embedding of P into the degree structure extend to an embedding of some Qi into the degree structure, where the I may depend on the particular embedding of P. So therefore, if I have one embedding of P into D, I may use KQ0, but if I have another embedding of P into D, I may have to extend it via to an embedding of Q1. Okay, so that is the general problem for deciding the Eae theory. And this is what you have to decide in order to give a full decision procedure for the Eae theory. It's not a very hard argument to show this is equivalent, so I'm going to skip this, but you can look it up, for example, in Lerman's book. Now, how is this applied in the, so remember, of the 6 examples I gave you, 3 of them had an Eae theory which was known to be decidable. For the M degrees and for the CE M degrees, Joktiv used the following fact. He said he used the fact that a finite partial order P can be minimally extended to a finite distributive lattice L. And remember, the M degrees and then the CE M degrees form a distributive upper semi-lattice, so therefore, you only need distributive lattices. So P can be extended in a minimal way to a finite distributive lattice L. So I can assume right away that P is really already a finite distributive lattice. And now I'm embedding this L as initial segment, as we saw earlier already. And then an embedding of L can be extended to embedding of some finite partial order Qi extending L exactly when no element of Qi is below any element that already exists in L, because after all, L is initial segment. I can't shove anything underneath an element that's already in L, in the range of L. And secondly, Qi respects a join in L. So if some element in Qi is above two elements in L, then it's also above the join of these two elements in L. Okay, so this gives a nice decision procedure for the Eae theory for the many 1 degrees and the CE many 1 degrees. And for the Turing degrees, Lerman and Shor proceed quite similarly, but instead of having L a finite distributive lattice, they used L being a finite lattice, possibly non-distributive, which again minimally extends P. But it's the same kind of argument. Okay, so that's the Eae theory for these three structures. Now there were three structures, recall, that I also mentioned, where we only know the Eae theory to be decidable, but not for the Eae theory. And let me tell you about what the obstacles are. So typically, when you want to decide the Eae theory, the first two problems you will attack are the following two subproblems. One of them is called typically the extension of embeddings problem. And this is a special case of the problem I mentioned on the last slide, where instead of worrying about extending an embedding of P to an embedding of some Qi, you just worry about an extending of a finite partial order P to a single extension Q, which is again a finite partial order. And then the question is, does every embedding of P into this degree structure extend an embedding of Q into the degree structure? Okay, so that is the one problem. The other famous subproblem of the Eae theory is what's often called the lattice embeddings problem. And this is a problem which finite lattice of L can be embedded into D. Now, when I say lattice embeddings, I mean really that it's not just an embedding of L as a partial order, but as a lattice. So you also preserve the join and the meet in L. So these are the two subproblems you have to solve, certainly, before you can have any hope of deciding the full Eae theory, because both of them are clearly subproblems of the Eae theory. That's clear for the first problem. For the second problem, with lattice embeddings problem, I mean, all you do basically is, use the Qi to test whether you preserve joins and meets, and that's how it's clear that this is again a subproblem of the Eae theory. So the extension embeddings problem now is decidable for the CE Turing degrees. This is work that was done by Slayman and So around 2000. It was actually done in the late 90s, but it was published only in 2001. For the enumeration degrees, this was actually done very recently in the same paper that I already mentioned of Slayman, Sosko, and myself that was just submitted. So this is a new result. And for the sigma 02 enumeration degrees, this is an older result of Slayman, Sorby, and myself from 2005. So we showed in each case that there is a decision procedure for the extension embeddings problem. Each of these decision procedures is actually rather complicated. I mean, this is, this is not something that I can put on one. I mean, I could put on one slide, but it would really fill one slide completely. And so therefore, I would refer you just to read in the papers if you want to understand what these decision procedures are like. But they're quite complicated. I mean, they're multi-step decision procedures, but it is at least decidable. Given P and Q, I can decide whether every embedding of P extends to embedding of Q. So we have that for these three degree structures for which we do not know the full Eae theory to be decidable, at least we know the extension embeddings problem is decidable. The situation is worse as far as the lattice embeddings problem is concerned. So famously, the last embeddings problem remains open for the Eae Turing degrees. In fact, this has been open for and studied by many people for the last 50 years. And in fact, there hasn't been any progress in the last 20 years, as far as I know. The last paper that really mentioned new result, as far as I know, is a paper from 2000 by Lerman, which was based on the work of Lerman and myself from the late 90s about a new non-embeddable finite lattice. But this is really the major obstacle to deciding the Eae theory for the Eae Turing degrees. For the enumeration degrees, it is also open whether or not the last embeddings problem is decidable, but this is probably more for the lack of trying. In fact, it is quite possible that the techniques that Slayman, Soskov, and I developed recently for the Eae theory and the extension embeddings problem can also be used to solve the last embeddings problem, but we're still working on this, so this is work in progress. But so far, no claims should be made. Finally, for the sigma 02 enumeration degrees, this is again decidable. The last embeddings problem is decidable, and this is a very simple decision procedure because all finite lattices actually embed into sigma 02 Turing degrees. This is a result of mine with Andreas Sorby, published in 2002. In fact, we can do even better. We can actually embed all finite lattices preserving 0 and 1, meaning that the 0 of the lattice gets mapped to degree 0, and the 1 of the lattice gets mapped to the degree 0 prime. Okay, so we have a full decision procedure. So let's see. I think this is all I have to say at the moment. So therefore, I'd like to thank everybody for their attention, for coming. Fortunately, travel time is a little less these days. So spasiba and rakmet. And happy World Logic Day. And everybody stay safe until we're all vaccinated and can meet again in person.
Thank you. Any question?
Actually, I have several questions. Can I ask?
Yes, please, Mars.
First is a very short question. Your recent result with Ted and Maria, is it much more difficult than Eae decidability of Eae for Turing degrees?
Well, okay, so you mean the Eae theory now?
Yes, for all enumeration degrees. Is it much more difficult for the?
Well, it's I mean, it is I mean, it is a somewhat difficult priority argument because what we have to show is that every finite distributive lattice can be embedded as an interval, right? So I mean, in fact, we were showing actually even more. I mean, the technical result that we're showing for this in this paper, I mean, you can look it up, it's on my webpage, but the technical result that we're showing is the following. There are degrees A less than B for any finite distributive lattices. There are degrees A less than B such that any degree which is below B is either in the range of this lattice embedding, so it's between A and B, or it is actually strictly below B. So it's sort of a strong minimal cover kind of property, where the strong minimal cover is not just for the two-element lattice, but actually for an arbitrary finite distributive lattice. So any finite distributive lattice L, we can embed such that it is exactly the range of the interval from A to B, and anything which is less or equal B is actually either in the interval from A to B or strictly below A. And that gives us also the other result with some, you know, I mean, for the extension embeddings problem, we use the same technique, but now we have to add a little more things about how we can now extend things. That gives us a way to extend things more in, you know, going outside. Anyway, so that's the rough idea behind this.
Thank you. And the second question is, so in the talk we considered different reducibilities, like starting from M degrees, then going to Turing degrees. And is it reasonable to conject that, for example, for all these degree structures, like Eae theories are decidable and Eae theories are not decidable?
Well, I mean,
is there any examples of opposite?
Right. I mean, so it's reasonable to conjecture, and at the moment, I know of no counterexample for natural degree structure where either the Eae theory is undecidable or the Eae theory is known to be decidable. But of course, that's just a heuristic argument. I just say that we don't know of any counterexample to this dividing line. But there are examples like the three I mentioned, where we don't know the dividing line really is there. We just know the dividing line is somewhere between 1 and 3, but we don't know whether it's between 2 and 3. It could also be between 1 and 2, for example, for the C Turing degrees, or for the enumeration degrees, or the sigma 02 enumeration degrees. We just don't know. But the conjecture is that the dividing line is always between 2 and 3. And there are other degree structures. I mean, there are many other degree structures, for example, for WTT degrees. If you look at the CWTT degrees, I believe that we just know that the 4 quantifier theory is undecidable and the 1 or 2 quantifier theory is decidable. So there are other degree structures where we don't know that the 3 quantifier theory is decidable, is undecidable. Okay, so therefore, all we really know is that among the degree structures that have been studied, the dividing line seems to be somewhere between 2 and 3, but sometimes we don't have sharp bounds from either side.
Thank you. And maybe the last question is: there any approach to study, for example, Turing degrees via WTT degrees? I mean, some systematic way. For example, we don't prove something for Turing degrees, but instead we prove something for WTT degrees. Then we know some good distribution of WTT degrees inside Turing degree, and then do some.
Well, okay, so actually, so there has been some work using results about WTT degrees and applying them to the Turing degrees, but for the particular topic of decidability, I think this is probably not going to be that useful. I mean, there are results from WTT degrees that that also point in the same direction. But you have to remember that for WTT degrees, we have a distributive upper semilattice. So algebraically, it's a very different degree structure.
Mm-hmm.
Right. So you can't just say, okay, the result carries over, right? I mean, you have to use very different techniques for WTT degrees than for Turing degrees.
Yes, but of course we don't transfer directly, but we, for example, analyze like several patterns of distribution of WTT degrees within Turing degree, and
right. But remember, in order to use, say, Nice transfer lemma, or to study this problem for deciding the Eae theory, you really need to know what all the finite substructures are, and particularly to know what the intervals look like, etc. And I mean, it makes a huge difference whether or not a degree structure is distributive or not as an upper semilattice. So I think that the transfers of results for decidability and undecidability between WTT degrees and Turing degrees are probably not as helpful as for other as other techniques, because they're just too different, right? Just like the M degrees are also very different. They're again distributive, whereas the Turing degrees are not, and also the enumeration degrees are not distributive. I think distributivity makes a huge difference, and generally, when you have a decision procedure, I mean, the first thing you want to know for decision procedure is Lazarbayev problem, for example, right? And Lazarbayev's problem, of course, mentions whether or not the structure is distributive, because you cannot embed a non-distributive lattice as a lattice into a distributive upper semilattice. It's not possible.
Mm-hmm. Yes, thank you.
Yeah, you're welcome.
Okay, more question? Yes.
Hello.
Hi.
Stefan. Stefan, you mentioned the problem of embedding of lattice into the C degrees. What about DCE and C degrees? Which is it more easy problem or more
That
complicated?
is a very good question. So for the DCE degrees, actually, we have a very interesting situation that there is no finite lattice which is known to be non-embeddable. So it is consistent with current knowledge that every finite lattice is embeddable into the DCE degrees, DCE Turing degrees. In fact, Downey and Shore at one point thought they had a proof, and then the proof fell through, unfortunately. This was somewhere about 20, 25 years ago. But we really don't know the answer. And it's a very interesting question, but I mean, we do know that there are quite a few lattices which are not embeddable in the CE Turing degrees that are embeddable in the DCE Turing degrees. For example, this famous lattice S8, right? That Lachlan and Soar showed to be non-embeddable in CE Turing degrees. It's actually embeddable into the DCE Turing degrees. But basically, it's just that people haven't tried hard enough, I think, you know, well, I mean, certainly Downey and Shore tried hard for a couple of years, but I think not enough people have tried, you know, to see whether or not the lattice-based problem for the DCE Turing degrees can be solved. That's a very interesting question. I mean, in fact, that kind of hurts me to ignore the DCE Turing degree because it's one of my favorite structures, but I just simply didn't have time and space on my slides to introduce yet another degree structure, which is probably somewhat less well known as the other degree structures I was talking about.
Okay, thanks.
You're welcome.
Okay, Vadim Puzarenko.
Thank you. Hi, Stefan. It's Boha here. Yeah, sorry.
Sorry.
Hi.
Hi.
So actually, yeah, when you talk about the DCE embedding, that is embedding, S8 is already learned to be embeddable, right?
It's what? I'm sorry?
S8.
Yes, S8 is known to be embeddable, right? Yeah, that was shown. Actually, I think this was shown by my student Kadar in.
Yeah. I think that is done by using something like
Yeah.
Mm-hmm. Yeah. And how about the other techniques like bi-interpretability for this kind of the lattice embeddings?
So okay, so you mean by interpretability to show that you can code arithmetic into the
yeah.
I know less about that. I mean, you would probably have to ask other people who are much more familiar. I see Maria's in the audience. She'd be able to tell you much more about this than I can.
Yeah. Okay.
So yeah, so maybe I haven't really worked much on the coding of arithmetic into degree structures. I'm more interested in fragments and in finite substructures because that seems to be more along my line of thinking.
Okay, thank you for nice talk. Yeah.
Thanks.
Okay. Vadim?
Excuse me, Stefan. Could you give the estimation of the complexity levels in probably arithmetical hierarchy for some considered semi-lattices? Excuse me, for Eae theories.
I see. Right. That's actually a problem which has not been studied, unfortunately. So I mean, obviously, it's not true that the Eae theory is zero prime computable just because the Eae theory is decidable, right? I mean that obviously doesn't fall through. That doesn't work. On the other hand, if you look at the complexity of the reducibility. So Turing reducibility is, for example, for the, let's look at the CE Turing degrees, for example. Turing reducibility on the CE Turing degrees is sigma 0.4. So therefore, it takes 4 quantifiers to decide whether something is reducible. And then if you add 3 more quantifiers for the theory, so therefore you get 0. So therefore the Eae theory is computable the oracle 0 to the 7. I don't think anybody has studied whether or not there's a better bound. And this would be, again, be an interesting question. People have asked me at times, but nobody has really seriously worked on that particular problem. It's a good question. I don't know about the Turing degrees in general. I mean, I don't even, yeah, I mean, yeah, it's a very good question, but I don't know the answer. I mean, it also has been studied for M degree, right? For M reducibility, for example, for the CEM degrees, reducibility is sigma 0,3, so therefore you get 0 to the 6 can actually decide the Eae theory. That's an upper bound in the complexity, but we don't know any better upper bounds. It would be nice to get better upper bounds, but I just don't know.
Thank you.
Okay, any other question, comment? Okay, so if no comment, then me and Nicola will thank all the speakers and with nice talk, and thanks all of you to joining today's workshop.
No, thanks for organizing this workshop.
Thanks for the nice talk, and have a nice day. Stay safe. Kolya, if you want to say something.
I'd like to thank all the speakers for very good talks, and also I would like to thank all the participants for joining us at this like either early hour or late hour. Yeah. Okay. Thank you.
Ah, you can see.
So,
Thank you.
Yes.
I guess I have, there's a result that the pi5 theory of any interval in the CE degrees is undecidable. So it's a little better than 7. So this is an old paper of mine and Klaus Sambo-Spies.
Hold on, but Richard, what you're talking about is the decidability of again another local degree structure. I think Vadim's question was about the complexity of the theory. So take the Eae theory as a set of formulas, and now ask about the complexity of that set of formulas. And an upper bound for CE Turing degrees, for example, is 0 to the 7. But I don't know if anybody has ever has ever established a better bound.
Oh, so you can get. I have to let you. You can get some bounds from the bi-interpretability results.
But is it really better than 0 to 7?
I don't know. I have to go look.
You would have to count pretty hard. I mean, certainly.
I think I once counted quantifiers, but I don't.
Almost certainly, it wouldn't be the optimal bound that one would hope for.
Oh no, it was a ridiculous bound.
Right. I mean, well, 0 to 7 is already not that bad a bound, right? I mean, I think if you look at the coding arithmetic, you usually get like 16 quantifiers, something like that, right? I mean,
yeah, 10 or yeah.
Okay, right. So a large number, right? Whereas 0 to 7 is actually not too bad, right? Anyway.
Yeah. Okay. I don't remember.
I believe that the decoding lemma gets you to 5 quantifiers.
Yeah.
Okay.
I think.
Sorry.
Yeah. Okay, I'd have to go look. I don't know.
Okay. More comment? No questions, no comments. Okay, great. So thanks again, and have a nice night, and have a good day for America.
Thanks.
Yes.
Thank you.
And good morning.
Thank you to the
Thank
speakers.
you.
Thank
Goodbye.
you for organizers.
Yes. Good
Thanks very
night.
much.
Okay.
Bye-bye.
Bye-bye.
Bye.